You may think the most dangerous thing in the universe is a black hole, a supernova, or an exploding star. But what if the real danger is the thing everywhere at once? The silence between stars, the space inside atoms, the vacuum beneath reality itself. And if you enjoy calm science that makes you think deeply, don't forget to like the video. In this video, we explore why empty space might be the most dangerous thing in the universe. Not because it attacks, but because everything depends on what it quietly is. Empty space looks peaceful, but it may be the most powerful thing in reality. You might think the most powerful things in the universe are the ones that announce themselves with violence. A black hole bending light into a ring, a supernova tearing a star apart, a galaxy collision spreading fire across millions of years. But the deeper mystery may be quieter than all of them, because it waits in the places where you think nothing is happening. Empty space looks peaceful because it has no surface, no color, no voice, no obvious shape for the mind to hold. It seems like the silent gap between real things, the background after the actors have left the stage. But physics has slowly taught us something stranger. Space is not the same as absolute nothing. Even in a perfect vacuum where there are no air molecules, no dust, no planets, no visible matter at all, the fabric of space-time is still there, and the invisible fields of nature are still there, and the rules that allow particles, forces, atoms, light, and time to behave as they do are still quietly in place. In modern physics, particles are not best imagined as tiny beads floating through emptiness, but as disturbances in fields that fill space, a little like ripples rising on a surface you cannot see. An electron is connected to an electron field. Light is connected to the electromagnetic field. What we call matter may be the visible trembling of something deeper. So the emptiness between stars is not a dead absence. It is more like a hidden foundation, so calm on the surface that it almost fools you into thinking it is powerless. And yet, this invisible foundation can leave measurable traces. In the Casimir effect, two extremely close metal plates can feel a tiny force because the vacuum between them behaves differently from the vacuum outside them. In the Lamb shift, the energy levels inside atoms are subtly changed in a way that helped reveal how the vacuum is not simply blank. These are not myths, not dramatic exaggerations, not bedtime monsters invented to make space sound frightening. They are careful experimental clues that the quietest thing in the universe can still shape the behavior of matter. And when you let that idea grow larger, it becomes even more unsettling. If empty space has properties, then those properties do not only matter inside laboratories or atoms, they may matter across the entire cosmos. The expansion of the universe is accelerating, and one of our best descriptions points towards something associated with space itself, something we call dark energy. Not because we understand it fully, but because we can see its effect in the way distant galaxies are carried farther away as space stretches. The more space there is, the more this strange influence seems to matter. So the void is not merely the emptiness between objects. It may be part of the reason the future universe becomes colder, darker, and more distant. Then comes the most delicate idea of all. In some theories, the vacuum of our universe may not be the final, deepest possible state. It may be stable, or it may be only temporarily stable in a way physicists call a false vacuum. That does not mean a disaster is expected tomorrow, or that you should be afraid while lying in bed tonight. It means something more thoughtful and more profound. The thing we casually call empty space may be tied to the hidden stability of reality itself. If the vacuum were different, the rules of particles, forces, and atoms could be different too. The world you trust, the solidity of your hand, the glow of a star, the distance between galaxies, even the long future of time, may depend on properties of space that you never see and almost never think about. And that is why empty space can be called powerful without turning it into a monster. It does not chase you. It does not roar. It does not explode in the sky. Its power is quieter than that, deeper than that, and perhaps more important than that, because it is everywhere. The smallest feature of the vacuum can whisper into atoms. The largest feature of space can guide galaxies beyond reach. So when you look into the darkness between stars, do not imagine a blank hole in reality. Imagine the invisible ground beneath everything, the silent rulebook that matter obeys without knowing it, the calm ocean on which all visible things briefly rise and fall. The greatest secret of the universe may not be hidden inside the stars at all, but in the silence between them. In the empty place that was never truly empty, the universe is mostly empty, and that is the strange part. If you could step outside your body and watch the universe shrink into a model small enough to hold in your hands, the strangest thing would not be how much there is, but how little. At first, the universe feels crowded in your imagination. Stars burning everywhere, planets circling, galaxies turning like slow luminous wheels, dust clouds glowing in the dark. But when you begin to measure the distances between these things, the picture changes into something far more unsettling. Matter is rare. Space is the rule. A galaxy may contain hundreds of billions of stars, yet the distances between those stars are so vast that even inside a galaxy, most of the volume is emptiness. If the sun were reduced to the size of a small fruit, the nearest star would still be thousands of kilometers away on that same scale. The night sky looks full because light travels across enormous distances and gathers in your eyes like ancient rain. But the places between those lights are wider than the mind wants to admit. And this emptiness is not only out there between galaxies, it is also inside the things you call solid. Your hand, the chair beneath you, the floor holding you up. All of them are made of atoms, and atoms are mostly empty space. The nucleus is incredibly tiny compared with the whole atom, while electrons occupy regions around it in ways that are not like little planets on neat tracks, but more like clouds of possibility shaped by quantum rules. So why does anything feel solid at all? Not because matter is packed tightly like stone all the way down, but because forces and quantum behavior prevent atoms from simply passing through each other. When your fingers press against a table, you are not feeling a perfectly filled object. You are feeling interactions, resistance, the invisible refusal of one arrangement of matter to collapse into another. Solidity is not the absence of emptiness. Solidity is emptiness organized by rules. That is the strange part. The universe is not a warehouse full of objects sitting in a container. It is more like a vast structure where tiny islands of matter are separated by oceans of space. And yet those islands can form stars, chemistry, planets, bodies, eyes, and thoughts. On the largest scales, galaxies gather into clusters and filaments, stretched along the cosmic web, while enormous voids sit between them like dark rooms in the architecture of reality. These cosmic voids are not small gaps. They can span millions of light years, containing far fewer galaxies than the brighter regions around them. If you imagined the universe as a glowing city, most of it would not be streets or buildings, but the quiet distance between neighborhoods. And somehow, from this overwhelming emptiness, structure appears. Gravity slowly draws matter together. Gas collapses into stars. Stars forge heavier elements. Dead stars seed space with the ingredients of worlds. Worlds cool. Chemistry becomes complex. Life begins asking why there is anything here at all. This means emptiness is not a failure of the universe to be complete. It may be the condition that allows complexity to exist. Without space between things, there would be no orbits, no motion, no room for stars to form, no distance for light to travel, no time for structures to unfold. Too much matter packed everywhere would make the universe chaotic, hot, and crushing. Too little structure, and there would be no stars, no planets, no observers. We live in the tension between almost nothing and just enough. That is what makes the emptiness so profound. It is not merely a blank background behind existence, but part of the reason existence has shape. The universe is mostly empty, yes, but that emptiness is not meaningless. It is the silence that gives the music room to be heard. The dark between the stars that lets the stars be stars. The open space inside matter that allows matter to have form instead of becoming an impossible, featureless mass. So when you look around and see a solid world, remember how much absence is hidden inside it. When you look upward and see a crowded sky, remember how much distance lies between each point of light. The universe is not strange because it is full. It is strange because it creates so much from so little, building everything you know on a foundation that is mostly open, mostly silent, mostly empty, and yet somehow alive with possibility. Empty space is not nothing. Try to imagine removing everything from a room, not just the furniture and the walls, but every dust grain, every molecule of air, every beam of light, every trace of heat, until your mind says, "Now there is nothing here." And then realize that physics would still disagree. Empty space is not nothing, because nothing would mean no place, no time, no distance, no direction, no rules, no possibility for anything to happen at all. But a vacuum is different. A vacuum is still somewhere. It still has length, shape, duration, and the ability to contain events. If you place a clock in it, the clock can tick. If light passes through it, the light can travel. If gravity bends it, space-time can curve. That alone makes it more than nothing. This is one of the most important distinctions in modern physics, because the word empty tricks the mind into imagining absence, when it really means the lowest condition a region of space can have after ordinary matter has been removed. In laboratories, scientists create extremely good vacuums by pumping out air, but even those spaces are not perfect nothingness. A few particles may remain, radiation may pass through, the walls of the chamber still define a boundary, the laws of physics still operate inside, and even if you could remove every ordinary particle, you would not remove the deeper structure that allows particles to exist in the first place. This is why nothing in daily language and vacuum in physics are not the same idea. When people say outer space is empty, they usually mean it is almost empty compared with Earth's atmosphere. But the vacuum of space is not a blank eraser mark in reality. It is more like a stage with no actors currently standing in the spotlight. Yet the stage, the lighting system, the floorboards, and the script still remain. Something can enter. Something can move, something can change. Absolute nothingness could not do any of that, because there would be no there for change to occur. And this raises a deeper question. Has anyone ever experienced true nothing? Probably not. Every thought you have about nothing already gives it a kind of shape. You imagine darkness, but darkness is still a visual idea. You imagine silence, but silence still requires time in which sound is absent. You imagine emptiness, but emptiness still feels like a container waiting to be filled. Real nothing would be beyond image, beyond silence, beyond waiting. It would not be black, because black is still a kind of experience. It would not be quiet, because quiet is still the absence of sound inside time. It would not be endless space, because space itself would not exist. So when physics studies empty space, it is not studying pure nothingness. It is studying the most stripped-down version of something, and that stripped-down something may be one of the most revealing things in the universe. It tells us that reality does not begin with objects. Objects are late arrivals. Before stars, before planets, before bodies, before eyes that look upward in the dark, there must be a framework in which existence can unfold. The vacuum is part of that framework. It is not a pile of matter, but it is also not a total void. It is the quiet condition that remains when the obvious things are gone. And perhaps that is why empty space feels so difficult to understand. It sits between two words we think we know, something and nothing, and refuses to belong completely to either. It is almost absence, but not quite. It is nearly silent, but not meaningless. It is the place where the universe shows that being does not always need a visible form. So the next time you hear the phrase empty space, do not picture a dead blankness. Picture the thinnest layer of reality we can still call real, the invisible room in which light can cross, gravity can bend, time can pass, and matter can one day appear. Empty space is not nothing. It is what remains when the universe removes its mask and lets you glimpse the quiet structure underneath. The darkness between stars is full of invisible fields. The black space between stars is not empty because nothing is there. It is black because most of what is there does not shine in a way your eyes can see. When you look up at the night sky, your attention naturally goes to the bright points, as if stars are the real story and the darkness is only the pause between sentences. But modern physics asks you to reverse that instinct. The dark regions are not just gaps. They are crossed by invisible fields that stretch through galaxies, surround planets, guide charged particles, carry waves, and quietly connect distant places without ever becoming visible themselves. A field, in the simplest sense, is a condition spread through space. It does not need to look like smoke or water. It does not need to be made of tiny grains you can pick up. It is more like an invisible instruction present at every location, telling certain things how they would behave if they were there. A magnetic field can bend the path of a charged particle, even when the space looks dark. A gravitational field can shape the motion of a planet, even though no rope is pulling it. The electromagnetic field can carry light across the universe, allowing a star's ancient glow to travel for millions or billions of years before it reaches your eye. This means the space between stars is not a dead corridor. It is more like a silent landscape of influences, a hidden weather system of forces and relationships. In our own galaxy, magnetic fields thread through clouds of gas and dust, helping shape how charged particles move and how some cosmic radiation travels. Astronomers can detect these fields indirectly, not by seeing the field itself, but by watching what it does. How light becomes polarized as it passes through dusty regions, how radio signals twist on their journey, how energetic particles spiral instead of moving in straight lines. The field is invisible, but its fingerprints are written into the behavior of everything that crosses it. And this is where the idea becomes deeper than astronomy. The universe does not seem to be built only from objects floating in a blank container. It is also built from relationships that exist even when no obvious object is present. A planet is not only a planet, it is surrounded by fields. A star is not only a burning sphere, it shapes the space around it. A galaxy is not only a collection of stars, it is wrapped in vast patterns of gravity, magnetism, radiation, and motion. Even the darkness is structured. Even the silence has rules. You can think of visible matter as the music you hear, while fields are the invisible sheet on which the music is written. Without fields, light would not travel as it does. Planets would not hold their paths. Compasses would not point. Atoms would not interact. And the universe would lose the quiet language that lets one thing influence another across space. This does not mean the darkness is magical or conscious. It means reality is less object-like than it first appears. The world you see is only the bright surface of a deeper order, and that order can remain completely hidden while still being powerful enough to steer matter. In a way, the darkness between stars is humbling, because it teaches you that visibility is not the same as importance. The most obvious things are not always the most fundamental. A star may dominate your attention, but the unseen fields around it help determine how its light moves, how its particles escape, how its surrounding space behaves, and how it belongs to the larger galaxy. And perhaps this is why the night sky feels so quiet and yet so alive. You are not looking into a vacant darkness. You are looking through layers of invisible influence, through magnetic threads, gravitational curves, radiation fields, and deep physical patterns that never ask to be noticed. The stars are the lamps, but the darkness is the wiring. The light is what reaches you, but the fields are part of what makes reaching possible. So when you stare into the space between stars, do not imagine a simple absence. Imagine a hidden architecture too subtle for the eye. A vast invisible fabric where forces wait without form, where darkness is not emptiness, but the place where the universe keeps its deepest instructions. Particles may be ripples in empty space. A particle may seem like the smallest possible thing, a tiny grain of reality moving through space, but the deeper you look, the more that picture begins to dissolve. In the older imagination, the universe was made of little solid pieces, like invisible dust arranged into atoms, stars, bodies, and worlds. It was comforting because it made reality feel simple. matter was made of objects, and space was the place those objects moved through. But modern physics tells a stranger and more elegant story. What you call a particle may not be a tiny heartbeat at all. It may be a small, concentrated ripple in a field that exists everywhere. Not a ripple in water exactly, because there is no ordinary liquid underneath it, and not a ripple in empty air, because even air is made of particles. It is a ripple in a deeper physical field, one that fills space so completely that there is no obvious edge where it begins or ends. The electron is not unique because there is one little electron object hidden somewhere in the universe. Rather, every electron can be understood as an excitation of the same electron field. A photon, the particle of light, is an excitation of the electromagnetic field. Other particles are connected to their own fields as well. In this view, the universe is less like a box filled with tiny marbles and more like a vast, invisible ocean of possible vibrations, where what we call matter appears when certain fields are disturbed in precise ways. This helps explain one of the most mysterious facts about particles. They are all perfectly identical. Every electron in your body is indistinguishable from every electron in a distant star, not because nature manufactured endless copies from a mold, but because they are expressions of the same underlying field. It is like hearing the same note played in different rooms. The location changes, but the note belongs to the same musical structure. And when scientists smash particles together in accelerators, they are not merely breaking tiny balls into smaller balls. They are concentrating energy into a small region. And under the right conditions, that energy can excite fields and produce new particles. This is why matter can appear, transform, vanish into radiation, or emerge from energetic collisions without violating the deeper rules of physics. The stuff of the universe is not fixed in the way everyday objects seem fixed. It is dynamic, it is responsive, it can change form when energy moves through the hidden field structure of reality. Even the old question, is light a particle or a wave, becomes softer in this view. Light behaves like both because the field itself has wave-like behavior, but when it interacts with something, it often delivers energy in small packets we call photons. The particle is not a little pebble riding on a wave. It is the wave showing up in a countable way, and this is where the idea becomes quietly powerful. If particles are ripples in fields, then matter is not separate from what you call space. Matter is space made active. Matter is the hidden field becoming visible through disturbance. The atoms in your hand, the oxygen you breathe, the calcium in your bones, the iron in your blood, all of it may be described not as solid little bits placed inside emptiness, but as patterns of excitation in fields that reach across the universe. This does not make your body unreal, it makes it more astonishing. You are not a statue made of dead substance. You are a temporary arrangement of field activity, stable enough to remember a childhood, soft enough to feel loneliness, complex enough to wonder what you are made of. And the room around you, though it may look still, is not truly a separate stage from you. It is part of the same deep system, the same unseen physical order whose quiet excitations become particles, whose particles become atoms, whose atoms become chemistry, and whose chemistry eventually becomes a mind listening in the dark. So when you imagine empty space, do not picture a hollow container waiting for matter to arrive from somewhere else. Picture something subtler, a calm surface capable of carrying form, a hidden instrument capable of producing every note in the cosmic song. The particle is the note you hear. The field is the music before it becomes sound. And maybe the strangest truth is this: what you call something may simply be emptiness learning how to ripple. Even perfect vacuum is not truly still. Imagine finding the quietest place in all existence, a region with no air, no dust, no sunlight, no drifting atoms, no heat you could feel, no sound that could travel, and then discovering that even there, silence is not the same as stillness. A perfect vacuum sounds like the final pause of reality, the place where everything has been removed and nothing is left to move. In everyday life, this makes sense. Because stillness usually means the absence of motion. A room becomes still when people leave. Water becomes still when wind stops touching it. A body becomes still when it rests. But the quantum world does not follow that simple picture. In classical thinking, if you could take away every bit of energy from a system, you might expect it to become perfectly frozen, perfectly calm, perfectly motionless. Yet quantum physics places a strange limit on this dream. Nature does not allow certain properties to be pinned down with perfect sharpness at the same time. The deeper you go, the more reality resists becoming a completely fixed statue. Even when a system is in its lowest possible energy state, it is not the same as absolute dead stillness. Physicists call this lowest condition a ground state, and it can still carry what is known as zero-point energy. Not usable energy waiting like a hidden battery, not magic fuel, not a secret engine for impossible machines, but the unavoidable minimum activity that remains because quantum systems cannot be perfectly motionless in the way ordinary intuition imagines. Think of a pendulum in the everyday world. If you remove all motion, it simply hangs there. Now think of the quantum version of that idea. The lowest state is not a silent dot with no uncertainty at all. It is more like a quiet blur, a condition where the system is as calm as nature permits, but not reduced to a perfectly frozen point. This is why the phrase vacuum fluctuations is often misunderstood. It does not mean empty space is literally boiling like soup, with tiny particles constantly popping in and out as if they were little sparks in a dark fireplace. That picture can be useful as a loose metaphor, but it can also mislead. The more careful idea is that the fields and systems described by quantum theory have unavoidable uncertainty even in their lowest state. The vacuum is not a busy crowd of ordinary objects hiding in darkness. It is a quantum state with subtle, restless structure. And that restlessness is not something added on top of the vacuum. It belongs to the way the vacuum is defined. This matters because the stillness you see in the universe is often a surface impression. A cold object still contains atoms with quantum behavior. An atom in its lowest energy state is not a tiny solar system that has simply stopped moving. It remains stable because quantum rules give it structure. Electrons do not fall neatly into the nucleus, not because they are little planets choosing not to crash, but because their allowed states are shaped by deeper laws. Even at temperatures near absolute zero, where ordinary thermal motion is reduced as much as possible, quantum effects can remain. Experiments with ultra-cold matter have revealed forms of behavior that would be impossible if cold simply meant nothing is happening. Liquid helium, for example, can display strange quantum properties at very low temperatures, reminding us that removing heat does not erase quantum nature. The vacuum, then, is not restless in the way a storm is restless. It is restless in the way a held breath is still alive, in the way a sleeping mind still dreams, in the way a dark ocean may look smooth from above, while deep currents remain below the surface. This is the quiet lesson. Reality does not need visible motion to have inner structure. A perfect vacuum is not filled with ordinary matter, but it is also not a dead blank. It is the lowest hum of the physical world, the background condition that remains when almost everything familiar has been taken away. And perhaps that is why the idea feels so haunting. It tells you that stillness is not always emptiness. Calm is not always absence. The universe can appear silent while still obeying rules so deep that no eye can watch them directly. So when you imagine a perfect vacuum, do not picture a frozen nothingness, sealed and finished. Picture the closest thing nature allows to quiet. Not motionless, not chaotic, but suspended in a delicate quantum calm, where the last trace of activity cannot be removed because it is woven into what reality is. Even perfect vacuum is not truly still, and in that almost silence, the universe reveals one of its strangest truths. The deepest peace is not the absence of everything, but the presence of rules too subtle to see. Space can push, pull, and shape matter without being seen. A planet does not need to be touched to be guided, and that may be one of the strangest lessons space has ever taught us. You can look at Earth moving around the sun and imagine an invisible hand pulling it in a circle. But modern physics offers a deeper picture. The sun changes the geometry of the space and time around it, and Earth follows that curved geometry the way a rolling ball follows the shape of the ground beneath it. Nothing reaches out like a rope. Nothing grabs the planet with fingers. Yet the path bends. This is why space is not just an empty arena where matter performs. It can be part of the performance itself. In Einstein's view of gravity, massive objects do not simply sit inside space. They reshape space-time, and that reshaped space-time tells other objects how to move. The result feels like a pull, but underneath it is structure. You are not being dragged toward Earth by a visible chain. You are living inside a curved region of space-time where the natural path of falling objects points downward. Even standing still on the ground is stranger than it feels, because your body is being prevented by the floor from following the path it would naturally take through curved space-time. What you experience as weight is partly the resistance of the ground holding you away from that fall, and this invisible shaping does not stop with planets. Light itself, which has no ordinary mass, can have its path bent when it passes near something massive, because light also follows the shape of space-time. This is why astronomers can see gravitational lensing, where a massive galaxy or cluster bends and magnifies the light of objects behind it. The space around the mass acts like a silent lens, not made of glass, not polished by hands, but written into the geometry of the universe. Sometimes this bending reveals things we would otherwise miss. A galaxy hidden far behind another galaxy can appear stretched, doubled, or brightened because its light has traveled through curved space. So when scientists map these distortions, they are not merely looking at pretty cosmic accidents. They are reading the invisible shape of space itself. This is one way matter can be shaped without direct contact. The universe does not need to strike objects to influence them. It can change the roads they are allowed to travel, and those roads can be gentle or violent. Near Earth, the curve is mild enough to let moons orbit, satellites circle, and falling objects accelerate in a way we can measure. Near a neutron star or black hole, the curvature becomes extreme, and the difference in gravity between one side of an object and the other can create tidal forces powerful enough to stretch matter apart. Even the moon's gravity raises tides on Earth, pulling more strongly on the near side of our planet than the far side, causing oceans to bulge and move in a slow rhythm that has shaped coastlines, ecosystems, and human timekeeping for ages. This is not space acting like a monster. It is space acting like a hidden landscape, with slopes and valleys you cannot see but everything must answer to. In the solar system, spacecraft use these invisible landscapes to travel more efficiently. Engineers can send probes past planets and use gravity assists, allowing the motion of a planet and the curvature around it to alter a spacecraft's speed and direction. The spacecraft is not refueling in the ordinary sense. It is borrowing momentum through a carefully planned encounter, using the invisible architecture of gravity like a current in a river. There are also places called Lagrange points, regions where the gravity of two large bodies and the motion of an orbiting object can balance in useful ways. Telescopes and spacecraft can be placed near such regions because the invisible structure of gravity creates a kind of stable or semi-stable arrangement. Again, nothing visible holds them there. The guidance comes from relationships, from motion, from the shape of the gravitational environment. On larger scales, the same idea becomes almost overwhelming. Galaxies do not form as random piles of stars. Gas flows, falls, compresses, and heats under gravity. Matter gathers along invisible patterns, forming clusters and filaments across cosmic history. Space, through its geometry and the distribution of mass within it, helps decide where matter collects and where it remains thin. Even when the cause is unseen, the effects become visible. Stars ignite, galaxies rotate, clusters bind together, light bends, tides rise, spacecraft turn, and worlds stay in orbit. What makes this so profound is that your senses are not built to see the structure directly. You see the planet, not the curvature. You see the ocean tide, not the changing gravitational pull. You see the arc of light, not the invisible lens. You see motion and call it force. But the deeper story is that the universe has hidden shapes, and matter is always reading them. So when you think of space, do not imagine a passive emptiness waiting for objects to cross it. Imagine a quiet architecture that can guide without touching, bend without hands, hold without ropes, and reveal itself only through the paths things take. Space can push, pull, and shape matter without being seen, not because it is magical, but because reality is built from more than visible surfaces. The deepest influences are often silent. They do not announce themselves. They simply decide the curve of the road. And everything, from a falling stone to a beam of starlight, follows. Empty space quietly controls the fate of atoms. An atom floating alone in perfect darkness might seem free from the universe, but even there, with nothing touching it, nothing visibly pushing it, and no air around it, it is still not truly alone. This is the quiet surprise hidden inside the fate of atoms. Their behavior is not decided only by what they are made of, but also by the empty space around them. Imagine an atom in an excited state, carrying more energy than it can comfortably keep. Like a bell that has been struck but has not yet released its sound. You might expect it to simply decide on its own when to calm down, dropping to a lower energy state and sending out a photon of light. But in modern physics, that empty surrounding space is part of the story. The atom is coupled to the electromagnetic field, and even when no light is present in the ordinary sense, the field still has a lowest possible quantum condition. That condition affects what the atom can do. This is why physicists do not treat an atom as a tiny isolated machine sealed inside its own private reality. They treat it as something always in conversation with the field around it, even when the conversation is almost silent. In everyday language, we call the process spontaneous emission, as if the atom simply releases light by itself. But a deeper view says it is not completely alone in that act. The surrounding vacuum provides the possible patterns or modes into which the photon can be emitted. If those possibilities are available, the excited atom can relax and release light. If the environment changes those possibilities, the atom's behavior can change too. This has been shown in experiments with cavities, mirrors, and carefully controlled environments. Place an atom in a region where certain light patterns are enhanced, and it may emit faster. Place it where those patterns are restricted, and the emission can be slowed or altered. This is connected to what is often called the Purcell effect, and it reveals something deeply important. The lifetime of an excited atom is not only an internal property of the atom, it also depends on the invisible structure of the space around it. The emptiness becomes part of the clock. The vacuum helps decide how long the atom remains excited, how it releases energy, and what kind of light can escape. That should feel strange, because atoms are usually presented as the building blocks of matter, as if they are small independent things from which the world is assembled. But an atom is not merely a miniature object sitting in a blank room. It is a quantum system surrounded by fields, allowed states, probabilities, and environmental conditions that guide what happens next. Even the colors emitted by atoms, the spectral lines that allow astronomers to identify elements in distant stars, depend on the way atoms move between energy levels and release photons. Those lines are like signatures written in light, and they are one reason we know what stars are made of without ever touching them. But beneath that beauty is a quieter fact. For an atom to shine, it must exchange energy with the field around it. Light is not just a decoration added to matter. It is one of the ways matter communicates with space. This matters in chemistry, astronomy, lasers, clocks, and the technology of precision measurement. Atomic clocks, for example, depend on extremely stable transitions inside atoms, and those transitions must be protected from outside disturbances, because even tiny shifts can matter. Scientists go to great lengths to isolate atoms from heat, stray fields, collisions, and uncontrolled environments, because atoms are sensitive. They are not crude little stones. They are delicate quantum instruments, responsive to conditions that human senses would never notice. A nearby surface, a confined cavity, radiation from the environment, or the available electromagnetic modes can all change the way an atom behaves. And this does not make atoms weak. It makes them precise. It shows that the material world is woven from relationships so fine that nothing nearby is never a simple phrase. Around every atom, space is not a blank emptiness, but a set of permissions and limitations, a quiet arrangement of what can happen and how. This is why the fate of an atom can be influenced without any visible touch. An excited atom may wait, release light, shift its behavior, or respond differently depending on the invisible conditions around it. The vacuum does not act like a hand reaching in. It acts more like the acoustic shape of a room around a musical note. The same note sung in an open field, a cathedral, or a small chamber does not feel the same, because the surroundings decide how the sound can live. In a similar but far deeper way, the surroundings of an atom help decide how light can be born from it. And when you understand this, matter stops feeling like a collection of separate pieces. It becomes a dialogue. The atom and the vacuum, the particle and the field, the visible and the invisible, all of them participate. So the next time you imagine empty space around an atom, do not picture a lifeless gap. Picture a silent partner. Picture the hidden condition that helps determine whether energy stays locked inside matter or escapes as light. Picture the invisible room in which atoms keep time, change state, and reveal their identity to the universe. Empty space quietly controls the fate of atoms, not by shouting over them, but by shaping the possibilities available to them. And perhaps that is the most delicate kind of power. Not the power to strike, but the power to decide what can happen at all. The vacuum has energy, but physics still doesn't fully understand it. There is a strange kind of energy hidden in the idea of emptiness, and the most unsettling part is not that physics found it, but that physics still cannot fully explain what it should be. When you hear the phrase vacuum energy, it may sound like a contradiction, because a vacuum is supposed to be what remains after everything has been removed. No air, no dust, no ordinary particles drifting through, no obvious motion, no visible source of power. And yet, in modern physics, the vacuum is not treated as a lifeless zero. It is the lowest state of quantum fields, and that lowest state is not perfectly empty in the ordinary sense. It carries a kind of baseline energy, a minimum condition beneath which the fields cannot simply fall. This does not mean there is a secret fuel tank in space waiting to be opened, and it does not mean unlimited energy can be extracted from nothing. That misunderstanding is common, but it leads away from the real mystery. The true mystery is more subtle. When physicists describe quantum fields, the vacuum seems to have energy built into it. But when they look at the universe as a whole, the amount of vacuum-like energy that appears to affect cosmic expansion is incredibly small compared with what some simple quantum estimates would suggest. The disagreement is not a small rounding error. It is one of the deepest mismatches in all of physics, often called the cosmological constant problem. It is as if one side of nature whispers, "The vacuum should matter enormously," while the universe calmly replies, "It does matter, but only a little." And between those two answers, an enormous question opens. To understand why this is so difficult, you have to begin with a quiet shift in perspective. In everyday life, energy belongs to things. A moving car has energy, a hot cup of tea has energy, a stretched rubber band has stored energy. But in quantum field theory, fields are not just passive backgrounds for particles. They are the deeper ingredients from which particles emerge, and even their lowest possible states can have structure. The vacuum is not a stage after the actors leave. It is the stage at its most basic condition, and the stage itself may still have a cost, a tension, a value. In ordinary calculations, many different field contributions appear to add to the vacuum's total energy. Some of these contributions are linked to quantum uncertainty. Others come from the way fields settle into their lowest states. The problem is that if you try to estimate this energy too naively, the result is absurdly large compared with what cosmology allows. If the vacuum energy were truly as large as those rough estimates imply, Space would not behave the way we observe it behaving. The universe might expand wildly, curve differently, or fail to form galaxies, stars, and worlds like ours. And yet here you are, breathing in a universe that clearly found some delicate balance. Something is cancelling, suppressing, adjusting, or hiding the enormous number that the simplest reasoning seems to produce. But what? That is where understanding begins to thin out. Maybe different contributions to vacuum energy nearly cancel each other with breathtaking precision. Maybe a deeper symmetry once forced them to cancel, and that symmetry is broken in a way we do not fully understand. Maybe gravity responds to vacuum energy differently than our current theories assume. Maybe our calculation methods are missing a principle that will only become clear in a future theory combining quantum physics and gravity. Or maybe the value we observe is not selected by a mechanism at all, but by circumstance. In a vast landscape of possible universes, only regions with a small enough vacuum energy allow galaxies to form and observers to appear. This last idea is uncomfortable to many physicists because it can feel less like an explanation and more like an answer, shaped by the fact that we are here to ask the question. But it remains part of the conversation because the problem is so stubborn. The vacuum does not simply refuse to be understood. It refuses to fit neatly into the two greatest frameworks we have. Quantum theory is extraordinarily successful at describing tiny scales. General relativity is extraordinarily successful at describing gravity, space-time, and the large-scale universe. But vacuum energy sits at their border like a locked door. In quantum theory, it seems unavoidable. In gravity, energy should influence the shape and expansion of space-time. Put those ideas together, and the vacuum should have gravitational consequences. Cosmology suggests that something with vacuum-like behavior may be driving the accelerated expansion of the universe, the phenomenon we often describe through dark energy. But the measured effect is gentle on cosmic scales, not explosively huge. This is the ache at the heart of the mystery. The vacuum appears to matter, but not in the way our simplest theories predict. It is present but strangely restrained. It pushes on the story of the universe, but in a whisper where some calculations expected a thunderclap. And perhaps that is why this topic feels so profound. It reminds you that science is not a collection of completed answers stacked neatly on a shelf. Science is also the art of finding where our best answers do not yet agree. The vacuum has energy, but we do not know why its observed influence is so small. We do not know whether the value is fixed by a hidden law, balanced by unknown physics, shaped by the early universe, connected to the Higgs field or other fields, or pointing toward a theory beyond anything we currently have. Even the word energy becomes delicate here, because energy in an expanding universe and energy in quantum fields are not always as simple as the energy of a ball rolling downhill. The vacuum is not an object. It cannot be weighed like a stone or poured like water. It is a condition of fields and space itself. And when you try to make it speak in the language of both quantum physics and gravity, it answers in riddles. Still, the riddle is not empty. It guides real research. It shapes how physicists think about the early universe, cosmic inflation, dark energy, particle physics, and the possibility that the laws we know are only part of a deeper structure. The vacuum's energy may be tied to why the universe expanded so rapidly in its first moments, if inflation occurred. It may be related to why the expansion is accelerating now. It may be connected to why empty space has the properties that allow atoms, chemistry, stars, and observers to exist. These are not disconnected mysteries. They may be different faces of the same hidden question. What is the ground state of reality, and why does it have the value it has? The humbling part is that the ground beneath physics is not solid yet. We can measure astonishing things. We can describe particles with incredible precision. We can map the cosmic microwave background, observe distant supernovae, detect gravitational waves, and model the evolution of galaxies. Yet the emptiest thing in the universe still contains a number we cannot explain. That should not make science feel weak. It should make the universe feel deeper. A complete mystery is not the same as ignorance with no direction. It is a pressure point where knowledge is most alive. The vacuum energy problem tells us exactly where our understanding is strained. It says, here, Between the smallest fields and the largest cosmos, something important is missing. And that missing piece may one day change how we understand space, time, matter, and existence itself. So when you think of the vacuum, do not imagine a simple emptiness waiting quietly outside the real story. Imagine a question spread everywhere at once, beneath every atom, between every galaxy, inside every dark region where your eyes find nothing. There may be a subtle energy whose value helps decide the shape and fate of the cosmos. It does not glow. It does not announce itself. It does not behave like ordinary power, but it sits at the center of one of physics' greatest unfinished conversations. The vacuum has energy, and the fact that we still do not fully understand it may be one of the clearest signs that reality is not built from what is obvious, but from what remains mysterious, even after everything visible has been removed. The biggest mystery in physics may be hidden in empty space. The deepest unsolved question in physics may not be hiding inside a particle accelerator, or at the edge of a black hole, or in the first flash after the Big Bang, but in the quiet condition we keep mistaking for emptiness. That sounds almost backwards, because when the mind searches for mystery, it looks for extremes: the hottest fire, the densest star, the smallest particle, the most violent collision. But empty space is where all of those things quietly borrow their rules. Before a particle can behave like a particle, before a force can act like a force, before matter can have mass, before light can cross the dark between galaxies, there is something underneath it all. Not a substance in the ordinary sense, not a hidden fog, not a magical ocean, but a physical state of reality that tells the universe what kinds of things are possible. This is why the vacuum is not just another topic in physics. It may be the place where physics reveals its deepest incompleteness. In the Standard Model, which describes the known particles and forces with extraordinary success, empty space is not a blank background. It is the lowest energy arrangement of fields, and those fields do not all sit in the same kind of nothingness. Some fields can have values even when no particles are present. The most famous example is the Higgs field. You do not see it, you do not feel it as a wind, and it does not glow in the dark, but it is understood to fill space, and its non-zero presence is connected to why many fundamental particles have mass. That is an astonishing idea. Part of what makes matter behave as matter may come from a condition of the vacuum itself. In other words, the empty room is not merely holding the furniture, it helps decide what the furniture is allowed to weigh. This does not mean mass is an illusion, or that particles are imaginary. It means the properties of particles are not always self-contained. They can depend on the state of the fields that surround and define them. The electron has the same mass everywhere we have measured, because the vacuum state appears consistent throughout the observable universe. But now ask the deeper question: why this vacuum state? Why these field values? Why these particle masses? Why these forces? Why this particular arrangement of reality instead of another? Physics can describe many of these facts with stunning precision, but description is not always the same as explanation. It can tell us how the rules work, while still leaving us staring at the strange fact that the rules exist in this form at all. And that is where empty space becomes almost philosophical without leaving science behind. If the vacuum is a state, then perhaps it could have been a different state. In the early universe, when everything was far hotter and denser, the fields of nature may not have had the same settled arrangement they have now. As the universe cooled, it may have passed through phase transitions, somewhat like water changing into ice, except far more fundamental, not a liquid becoming solid, but the underlying fields of reality settling into new patterns. During these transitions, forces that are now distinct may once have been unified in a more symmetric state, and particles may have acquired their familiar properties only after the universe cooled into the vacuum we inhabit today. This means the world you know may not be built on timeless settings carved into existence forever. It may be built on a cosmic history, a sequence of deep changes in the vacuum itself. The familiar universe, atoms, chemistry, stars, bodies, eyes, memory, may be the result of the vacuum choosing, or settling into, one particular form after the fire of the beginning faded. But what chose it? Was it inevitable? Was it random? Was it one possibility among many? These are not questions that can be answered by imagination alone. They sit at the border of particle physics, cosmology, and the search for a deeper theory. Some ideas suggest there may be many possible vacuum states, each with different properties, like different valleys in a vast landscape. If reality settled into one valley, the particles and forces would have one pattern. If it settled into another, the universe might have different masses, different interactions, perhaps no stable atoms, perhaps no stars, perhaps no life capable of wondering about it. This does not mean we know there are other universes, and it does not mean we can freely choose the laws of physics like settings on a machine. It means our best theories sometimes point toward a strange possibility that what we call the laws of nature may depend partly on the vacuum state in which we find ourselves. That is a humbling thought, because it turns empty space into something like a cosmic constitution, not a visible object, but the hidden arrangement that determines what reality can become. And then there is gravity, the one great force that refuses to fit neatly into the same quantum language as the others. Quantum field theory works beautifully for particles and fields. General relativity works beautifully for space-time and gravity. But the vacuum touches both. Quantum fields have vacuum states. Space-time responds to energy. Gravity shapes the stage on which the vacuum exists. Yet the vacuum may also influence the stage through its energy and structure. When physicists try to bring these ideas together, the answers become difficult, sometimes even contradictory. This is why empty space may be hiding the biggest mystery in physics, because it is where our two greatest descriptions of reality are forced to meet, and they do not yet fully agree. At the smallest scales, the vacuum is quantum. At the largest scales, space-time is gravitational. Somewhere between those two languages, something deeper must exist, but we do not yet know how to speak it clearly. A complete theory of quantum gravity would need to explain not just black holes or the Big Bang, but what space itself is when examined at its most fundamental level. Is space-time smooth all the way down, or does it have a deeper structure? Is the vacuum truly fundamental, or is it an emergent state, like calm water emerging from countless molecules beneath the surface? Are fields the final ingredients, or are they patterns arising from something even more basic? These questions are difficult because the vacuum does not give up its secrets easily. You cannot hold empty space in your hand. You cannot cut it open. You cannot watch its deepest layer directly. You can only study what it permits, what it changes, what it stabilizes, what it hides. And yet, everything depends on it. If the vacuum state were different, the universe might not simply look different. It might be unable to build the kinds of structures that make observation possible. Atoms might not hold together in the same way. Stars might not burn with the same balance. Chemistry might not be rich enough for life. The difference between a universe full of meaning and a universe sterile and brief may be written into the quietest properties of space. This is why the mystery feels so large. The vacuum is not spectacular in the way a supernova is spectacular. It is not terrifying in the way a black hole is terrifying. Its power is more intimate. It is the hidden agreement that reality makes with itself before anything visible appears. And perhaps this is why the silence between stars can feel so deep when you really think about it. It is not merely distance. It is not merely darkness. It is the unresolved question beneath every object you have ever touched. Why these fields? Why this stability? Why this ground state? Why this universe? Physics has answered many questions that once seemed impossible. But empty space remains strange because it asks a question beneath all the others. What is the basic condition of reality when everything removable has been removed? Until we answer that, we may understand many things inside the universe without fully understanding the foundation that lets a universe exist. So the biggest mystery in physics may be hidden in empty space, not because space is secretly crowded with visible things, but because it carries the invisible choices of existence itself. It is the quiet background that may decide the masses of particles, the separation of forces, the stability of matter, and the bridge between quantum fields and gravity. And when you look into what seems like nothing, you may be looking toward the deepest unfinished sentence in science, the place where the universe has written its rules, but not yet explained why those rules are the ones we received. The Casimir effect, when nothing creates a force. Place two perfectly smooth metal plates extremely close together in a vacuum. Remove every ordinary push you can think of, and the plates may still feel a tiny pull toward each other, as if emptiness itself has learned how to press. This is the Casimir effect, one of the most elegant and unsettling demonstrations that empty space is not a simple absence, and also one of the easiest ideas to misunderstand if it is told too dramatically. Nothing here is reaching out like a ghost. Nothing is creating energy from nowhere. The plates do not move because a magical force appears in the darkness. What happens is subtler, cleaner, and in some ways more mysterious. When two conducting surfaces are placed very close together, they change the kinds of electromagnetic field patterns that can exist in the narrow gap between them. Outside the plates, more patterns are allowed. Between the plates, fewer are allowed because the boundaries restrict the field. That difference creates a tiny imbalance, and the result can be measured as a real force. In 1948, Dutch physicist Hendrik Casimir predicted this effect while thinking about quantum theory and electromagnetic fields, and later experiments confirmed that the vacuum can produce measurable consequences when boundaries are arranged with extreme precision. The key is not that nothing becomes something, but that what we call nothing is still governed by rules. Even the lowest possible state of the electromagnetic field has structure, and when you place objects inside that structure, you change what is allowed to happen there. Imagine a musical instrument with strings that can only vibrate in certain ways. If you shorten the string, the possible notes change. The Casimir effect is not exactly a sound, but the comparison helps. The gap between the plates becomes a kind of invisible chamber where only certain field patterns can fit. The empty space outside the chamber has a different set of possibilities. The plates respond to that difference. This is why the effect becomes noticeable only at extremely small separations. If the plates are too far apart, the imbalance becomes incredibly weak, lost beneath other influences. But when the distance becomes tiny, smaller than the width of a human hair by a vast margin, the effect can matter. It is delicate, but it is real. It tells you that a vacuum is not just a silent container. It can be shaped by boundaries, and once shaped, it can push matter in ways no ordinary sense can see. This should feel quietly revolutionary. In everyday life, force usually feels obvious. A hand pushes a door, wind bends grass, gravity pulls a stone downward. But the Casimir effect belongs to a different category of influence. Nothing visible crosses the gap. No air pressure remains if the vacuum is good enough. No obvious mechanical spring connects the plates. Still, the plates feel a force because the quantum field conditions around them are not the same everywhere. The universe is showing you that not all pressure comes from particles striking a surface like tiny bullets. Sometimes pressure comes from the difference between what a field can do in one region and what it can do in another. This is why the phrase, "when nothing creates a force," is powerful, but it must be handled carefully. The force does not come from absolute nothingness. It comes from the vacuum state of fields interacting with physical boundaries. The plates are essential. Their material properties matter. Their distance matters. Their shape, temperature, roughness, and conductivity can all affect the result in real experiments. Scientists must account for these details because the effect is so small that any careless explanation becomes misleading. And yet, even after the careful corrections, the central idea remains astonishing. Empty space, when constrained, can produce a measurable force between objects. This is not a philosophical mood. It is laboratory physics. In modern measurements, researchers use sensitive instruments to detect tiny attractions between surfaces, sometimes with plate and sphere setups. Because perfectly parallel plates are extremely difficult to align. They must control dust, electrical charges, vibrations, surface imperfections, and temperature effects. The fact that the Casimir force can be measured at all is a triumph of precision. It is like hearing a whisper through a storm. then realizing the whisper came from the structure of the room itself. And this whisper has practical importance too. At human scales, the Casimir effect is far too weak to notice. You do not feel your hands being pulled together by vacuum forces. Your furniture does not collapse inward because empty space is pressing on it. But at very small scales, especially in microtechnology and nanotechnology, tiny forces can become important. Components in miniature machines can stick together. Surfaces can attract in ways engineers must consider. And the physics of close boundaries becomes more than a curiosity. The smaller the machine, the more the quiet forces of the vacuum may enter the design. This means the Casimir effect is not just a strange footnote in quantum theory, it is a reminder that when technology becomes small enough, the hidden rules of empty space begin to move from philosophy into engineering. But perhaps the deeper lesson is not technological, it is conceptual. The Casimir effect changes the way you imagine emptiness because it proves that absence can have structure. A blank wall and a narrow hallway are both spaces, but they do not permit the same movements. A cathedral and a closet are both filled with air, but a voice behaves differently inside them. In a similar way, the quantum vacuum is not identical in every situation once boundaries are introduced. The space between the plates is not less real than the space outside them. It is simply restricted differently. The field has fewer available patterns there, and matter responds. That idea invites a larger shift in how you think about reality. The world is not made only from visible things colliding in visible ways. It is made from allowed possibilities, from constraints, from boundaries, from hidden conditions that determine what can appear, move, vibrate, or settle. Sometimes the most important feature of a system is not what fills it, but what it prevents. The plates create a narrow silence, and that silence is not neutral. It changes the balance. It pulls. This is why the Casimir effect feels almost like a lesson in humility. You may look into a gap and see nothing, but physics sees a set of rules. You may imagine emptiness as passive, but the vacuum knows the difference between open space and confined space. You may believe force requires contact, but the universe can write influence into the very permission structure of fields. And still, the effect does not need exaggeration to be beautiful. It does not prove free energy. It does not mean the vacuum can be mined like coal. It does not mean reality is magical. It means reality is more disciplined than magic and stranger than fantasy. Even emptiness obeys conditions so precisely that two plates can feel the consequence. If you sit with that thought for a moment, the meaning of nothing begins to soften. Nothing, in physics, is often not a true void, but a state with rules, a ground condition with hidden order, a quiet background that changes when the boundaries change. And if a narrow gap between two plates can reveal this, what else might the universe be hiding in places where our senses report silence? How many forces are not loud, not bright, not obvious, but still shaping the behavior of matter because the invisible rules of space allow them to? The Casimir effect does not shout its importance. It does not tear stars apart or bend galaxies into arcs. It simply brings two small surfaces together by a nearly silent imbalance in the vacuum. And in doing so, it teaches one of the deepest lessons in modern physics. Emptiness is not the absence of influence. It is a condition that can be shaped, restricted, measured, and felt. So when you imagine two plates floating close together in a dark chamber, do not picture empty space as a dead gap between them. Picture an invisible order being squeezed into a smaller set of possibilities. Picture the vacuum not as a monster, but as a rule book that changes when the room becomes narrow. And remember this quiet truth. Sometimes the universe reveals its deepest power not by adding something, but by showing that even what seems missing can still leave a force behind. The Lamb shift, how empty space leaves fingerprints on atoms. A hydrogen atom is one of the simplest things in the universe, and yet inside its simplicity, empty space managed to leave a mark so small that it changed physics forever. Imagine a single proton with one electron bound around it, the most basic atom nature can build, almost like the alphabet's first letter written in the language of matter. For a long time, Physicists believed they understood its energy levels with extraordinary confidence. The equations were beautiful. The predictions were precise. Hydrogen became a kind of testing ground for reality itself, because if your theory could not explain hydrogen, it could not be trusted with stars, chemistry, or the structure of matter. But then came a tiny mismatch, a shift so subtle that it could have been ignored by a less careful civilization. In 1947, Willis Lamb and Robert Rutherford measured hydrogen with microwave techniques and found that two energy states, which the best theory of the time had treated as essentially the same, were not exactly the same after all. One was slightly shifted, not by a dramatic amount, not enough to see with the eye, not enough to disturb the atom in any obvious way, but enough to reveal that something hidden had been left out. This tiny difference became known as the Lamb shift, and it was one of the great clues that the vacuum surrounding an atom is not a perfectly passive stage. It helped push physics toward quantum electrodynamics, one of the most successful theories ever built, a theory that describes how light and matter interact with astonishing accuracy. The remarkable thing is that the Lamb shift is not caused by a new planet, a secret particle in the ordinary sense, or some visible object pressing against the atom. It comes from the fact that the electron is not living in a silent void. It is coupled to the electromagnetic field, and that field has quantum behavior even in its lowest state. The electron also interacts with its own electromagnetic influence, and empty space can briefly behave as though it is filled with subtle possibilities that affect the electron's energy. One way physicists describe part of the story is through self-energy. The electron is not merely a clean mathematical point moving untouched through reality, because its interaction with the electromagnetic field slightly modifies how it behaves. Another part of the story involves vacuum polarization, where the space around a charged particle is not perfectly indifferent. Quantum effects slightly alter how the electric influence is distributed. These are not ordinary little balls popping in and out like sparks in a cartoon. That image is often used too carelessly. The real idea is more controlled. Quantum fields allow effects that slightly change the measured energy of an atom, and those changes can be calculated and tested. The Lamb shift is one of the places where those invisible corrections become visible through precision. It is like hearing a single note from a violin and realizing the room around it has changed the sound by a fraction so delicate only the finest instrument can detect it. The atom is the violin, the vacuum is the room, and the Lamb shift is the tiny change in tone that proves the room was never irrelevant. To understand why this mattered so much, you have to remember what atoms are actually doing. An atom does not emit or absorb light randomly in any amount it wants. Its electron can occupy certain allowed energy states, and when the atom changes from one state to another, it can release or absorb light with a specific color or frequency. These patterns are called spectral lines, and they are among the most important fingerprints in all of science. They let us identify elements in distant stars, measure motions in galaxies, test physical laws, and build technologies based on atomic precision. So if the energy levels inside hydrogen are shifted, even slightly, that shift is not just a small correction in a textbook. It is a message from the deeper structure of reality. It says, the atom is not only shaped by the attraction between electron and proton, it is also shaped by its relationship with the quantum field around it. Before the Lamb shift was measured, one of the great achievements of physics was Dirac's theory of the electron, which combined quantum mechanics with special relativity and explained many features of atomic behavior. But Dirac's theory predicted that certain hydrogen states should have the same energy. Lamb's experiment showed they did not. That small disagreement was not a failure to be hidden. It was a doorway. It told physicists that the electromagnetic field itself had to be treated quantum mechanically with more care. It helped reveal that the vacuum was not merely a backdrop, but an active participant in the most precise details of matter. And this is the beautiful pattern of science. Sometimes the universe does not overturn your understanding with a giant explosion. Sometimes it does it with a decimal place. A tiny measurement, if it is honest, can break open an entire world. The Lamb shift taught physicists to take the invisible seriously. It showed that even the cleanest, simplest atom is surrounded by effects that only appear when your instruments become sensitive enough and your theory becomes humble enough. And that humility matters, because the story of the Lamb shift also warns us against trusting everyday intuition too much. You might think an atom in empty space is isolated, like a watch sealed in a glass case. But at the quantum level, isolation is rarely absolute. The electron's allowed states are influenced by its interaction with fields. The vacuum does not shout, but it adjusts. It does not grab the electron like a hand, but it changes the accounting of energy in a way that can be measured. That is why this effect deserves its poetic name as a fingerprint. A fingerprint is not the person. It is a trace left behind, a pattern small enough to miss, but specific enough to identify presence. The Lamb shift is the vacuum's fingerprint on hydrogen. It is empty space saying, not loudly but unmistakably, "I was here." And from that quiet trace came a deeper confidence in quantum electrodynamics, a theory so precise that some of its predictions match experiments to an almost unbelievable degree. Yet the emotional weight of the Lamb shift is not only in precision, it is in what precision reveals. When you look at a glass of water, a breath of air, a hand resting in moonlight, you are seeing matter that depends on atomic structure. Atomic structure depends on energy levels. Energy levels are not purely private properties of atoms sealed away from the rest of existence. They are touched subtly by the fields and vacuum conditions around them. This means the visible world is balanced on invisible corrections. The colors of light, the stability of atoms, the accuracy of clocks, the way matter announces itself to the universe, all of it is tied to details too fine for human senses, but not too fine for nature. There is something almost meditative in that. The world feels solid because your mind is built to survive at human scale, but underneath that solidity is a quiet negotiation of interactions, corrections, and allowed states. The Lamb shift is one of those places where the negotiation becomes audible, not to the ear but to measurement, not as a sound but as a difference. And in that difference, empty space becomes less like a blank page and more like a paper so textured that even the smallest ink line changes as it touches it. This does not mean the vacuum is mystical. It does not mean atoms are guided by consciousness or that empty space has intention. The power of the Lamb shift is precisely that it does not need fantasy. The real explanation is already strange enough. Fields, charges, quantum corrections, self-interaction, vacuum polarization. These are difficult ideas, but their meaning can be felt simply. The background is never completely innocent. What surrounds a thing can help define what the thing becomes. And perhaps that is why this discovery still feels profound decades later. It reminds us that the universe is not only built from dramatic structures like stars and galaxies, it is also built from small, nearly hidden shifts that keep the entire architecture consistent. A tiny change in hydrogen helped refine our understanding of light and matter. A slight mismatch became a revolution. A whisper in an atom became a new chapter in physics. So when you imagine empty space around matter, do not imagine a perfect silence with no signature. Imagine a silence sensitive enough to leave marks on the simplest atom. Imagine hydrogen, alone in the dark, carrying within its tiny spectrum the evidence that emptiness has structure. The Lamb shift shows that empty space does not need to become visible to prove it matters. It only has to move an energy level by the smallest amount, leave one delicate fingerprint, and wait for a careful mind to notice. Why virtual particles are more complicated than they sound. The phrase virtual particle sounds as if reality is secretly filled with tiny ghost particles, flashing into existence and disappearing before anyone can catch them. But that picture is only a shadow of the truth, and if you take it too literally, it can quietly mislead you. It is easy to imagine empty space as a dark room where pairs of particles constantly appear, borrow energy for a moment, and vanish again like sparks too fast for the universe to punish. This story is popular because it feels visual, dramatic, and simple. But nature is rarely simple at the level where quantum fields are doing their deepest work. In careful physics, Virtual particles are not ordinary particles with short lifetimes. They are not little balls that pop out of nothing, look around, and then disappear. They are features of a calculation, especially in a method called perturbation theory, where physicists describe interactions by breaking a complicated process into manageable pieces. In the famous diagrams used by Richard Feynman and others, real particles can enter and leave an interaction, while internal lines represent what we call virtual particles. But those internal lines are not directly observed objects. They are mathematical contributions to the probability of an event. They help physicists calculate what happens when electrons repel each other, when light interacts with matter, when particles scatter, transform, or exchange influence. The danger is that the drawing looks like a tiny story, as if one particle throws another particle like a ball. But the diagram is not a photograph of reality. It is more like a map of possibilities inside a calculation. A real particle is something that can travel away, reach a detector, and leave a measurable trace. A virtual particle cannot be isolated that way. You never catch one in a detector and say, "There it is." It belongs to the hidden middle of the process, not to the final list of things the experiment sees. This is why the word virtual matters. It does not mean fake in a useless sense, because virtual particles help produce predictions that match experiments with astonishing precision. But it also does not mean real in the everyday sense of a tiny object moving through space on its own. It is more subtle. Virtual particles are a language physics uses to describe how fields interact. And languages can be powerful without being literal. When two electrons repel each other, one common explanation says they exchange virtual photons. That sounds like one electron sends a tiny light particle to the other, causing it to move away. But if you imagine this too physically, questions quickly become confusing. Where exactly did the virtual photon travel? How fast did it go? Did it exist as a real photon? Could you detect it halfway? The careful answer is no. The virtual photon is not a detectable beam of light between the electrons. It is part of the quantum calculation that describes how the electromagnetic field allows charged particles to influence each other. The exchange is real in its consequences, but the virtual particle itself is not a little messenger you could intercept. It is more like an entry in the universe's accounting of interaction. Another source of confusion comes from the idea that virtual particles borrow energy from nothing because the uncertainty principle allows them to violate energy conservation for a short time. This is one of the most repeated explanations in popular science, but it is not the best way to think about it. Energy conservation is not simply thrown away whenever quantum mechanics feels strange. In serious quantum field theory, the overall process still obeys conservation laws. Virtual particles can be described as being off-shell, meaning they do not have the exact energy and momentum relationship required for real, freely traveling particles. But this does not mean the universe is casually breaking its own rules and hoping no one notices. It means the internal parts of a calculation are not constrained in the same way as the real particles you detect at the beginning and end. The final measurable event must still make physical sense. So when people say virtual particles appear because energy can be borrowed briefly, treat that as a rough metaphor, not a final explanation. It is a picture drawn for the imagination, not the machinery itself. The deeper machinery is fields, probabilities, interactions, and allowed outcomes. Virtual particles are one way to organize that machinery when the interaction is weak enough for the method to work well. This is also why different mathematical approaches can describe the same physical result without treating virtual particles as little things moving around. If a feature of reality depends heavily on the method you use to calculate it, you have to be careful before calling it an object. A chair does not disappear when you choose a different language to describe it, but a virtual particle is tied to a particular representation of the process. It is useful, meaningful, and predictive, but not a simple resident of space. It is closer to a hidden chord in a piece of music. You may not hear it alone, but it helps determine the harmony you finally hear. This does not make virtual particles unimportant. In fact, their importance is exactly why the idea needs care. The effects calculated using virtual particles help explain tiny corrections in particle behavior, the strength of forces, and the way interactions unfold at the smallest scales. They are part of the reason quantum electrodynamics became one of the most precisely tested theories in science. The mystery is not that physicists invented a meaningless trick. The mystery is that this strange calculation language works so well. It is as if reality allows us to predict its visible events by summing over invisible intermediate possibilities that never become ordinary things. That should make you pause. The universe may not be built only from events that happen in the clean, visible way our minds prefer. It may also be shaped by possibilities that contribute without ever stepping fully into the light. But again, you have to walk carefully here. Virtual particles are not proof that everything imaginable physically happens. They are not tiny spirits of potential. They are not evidence that empty space is a magical factory. They are a disciplined part of a mathematical framework, and their power comes from how accurately that framework describes experiments. This is where the idea becomes beautiful without needing exaggeration. Reality gives us observable outcomes. A particle changes direction, light is emitted or absorbed, forces behave with measurable strength, detectors click. Beneath those outcomes, the theory describes a field of possible contributions. Some are simple, some are more complex. Some include loops, corrections, and temporary internal structures that never appear as final particles. Virtual particles are names we give to parts of that hidden structure. They are the invisible grammar behind the sentence nature finally speaks. And perhaps the most important lesson is this: not every useful concept in science has to look like a physical object. Temperature is real, but it is not a little substance inside a cup of tea. A wave function is powerful, but it is not a glowing cloud you can touch. A virtual particle can be essential in a calculation without being a tiny marble moving through the darkness. This is hard for the mind because human imagination wants objects. It wants pictures. It wants a small thing doing a small action. But quantum field theory often replaces objects with relationships, processes, and probabilities. The real world we observe may be the finished surface of something far less object-like underneath. So when you hear that virtual particles fill the vacuum, pause before imagining a crowded invisible swarm. A better image is quieter. The vacuum is a quantum state of fields, and when those fields interact with matter or with each other, the mathematics of those interactions can be expressed through virtual contributions. The particles are not visitors passing through a room. They are part of how the room's deepest rules are written. And this is why the concept is more complicated than it sounds. It sits between metaphor and measurement, between picture and calculation, between what we can draw and what we can honestly claim exists. If you make virtual particles too literal, you turn physics into a cartoon. If you dismiss them completely, you miss one of the most successful tools ever created for understanding the microscopic world. The truth lives in the difficult middle. Virtual particles are not ordinary things, but they are not nothing either. They are shadows cast by the mathematics of interaction. And those shadows help predict the behavior of matter with breathtaking accuracy. Maybe that is the deeper lesson hidden inside the phrase. The universe does not always offer reality in the form of objects you can point to. Sometimes it offers traces, corrections, probabilities, and internal possibilities that never become visible alone, yet shape everything that finally appears. So the next time someone says empty space is full of virtual particles, do not imagine a storm of tiny ghosts. Imagine instead a deeper silence whose rules are so rich that even its unseen possibilities can influence what matter does. The mystery is not that little particles briefly cheat existence. The mystery is that existence itself may be woven from processes too subtle to be pictured, but precise enough to leave the world exactly as we measure it. The quantum vacuum is restless, but not magic. The quantum vacuum is often described as restless, but if you picture a dark emptiness sparkling with tiny miracles, you are already standing too close to the metaphor and too far from the science. The real vacuum is stranger than magic because it does not need to break rules to feel impossible. It is not a supernatural foam, not a secret engine, not a place where the universe cheats and creates things from nothing. whenever no one is watching. It is the lowest state of quantum fields, and that lowest state is not the same as a dead classical silence. In ordinary thinking, the lowest state of something should be perfectly calm. A stopped clock should stop. A cold stone should become still. An empty room should do nothing, but quantum theory changes what doing nothing means. At very small scales, fields are not like rigid objects that can be frozen into perfect certainty. They have built-in uncertainty, and that uncertainty gives the vacuum a subtle structure even when no real particles are present. This is why physicists speak about fluctuations, but the word can be dangerous if it is imagined too literally. A fluctuation does not always mean a little object physically appears, performs a tiny action, and vanishes like a magician slipping behind a curtain. More carefully, it means that the values of quantum fields cannot be treated as perfectly fixed and featureless in the way a simple classical picture would expect. There are correlations, uncertainties, and measurable consequences that reveal the vacuum has a kind of inner texture. But this texture is disciplined. It follows equations. It respects conservation laws. It does not give away free energy. It does not let you build a machine that pulls unlimited power from empty space. That is one of the most important truths to hold on to, because the vacuum is mysterious enough without turning it into fantasy. Many popular explanations make the quantum vacuum sound like a cosmic loophole, as if the universe is constantly borrowing from a bank and paying it back before anyone notices. But nature is not running a scam against itself. The vacuum is not a rule-breaking exception. It is one of the places where the rules become most precise. Its restlessness is not chaos. It is more like the trembling precision of a violin string that cannot be reduced to an infinitely sharp point, or the quiet uncertainty of a candle flame seen from far away, not wild enough to be a storm, but never identical from one instant to the next. And even these images are only bridges for the mind, not literal pictures. The real vacuum belongs to quantum field theory, where the basic ingredients of nature are fields spread through space, and particles are what appear when those fields are excited in certain ways. The vacuum is what remains when there are no such excitations present. But no excitations does not mean no field, and it does not mean no structure. It means the fields are in their most minimal condition. That minimal condition can still have observable influence, not because the vacuum is alive, but because the lowest state of a quantum field is not the same thing as an empty box in everyday life. This difference matters deeply. It prevents us from confusing mystery with permission to believe anything. The quantum vacuum does not prove that consciousness creates reality. It does not prove that thoughts can command matter. It does not prove that the universe is full of hidden spiritual particles waiting to answer desire. Those ideas may sound emotionally attractive, but they are not what the science says. The science says something quieter and more powerful. What looks like empty space is governed by quantum fields, and the ground state of those fields has properties that can be studied, calculated, and tested. That is enough. It does not need decoration. In fact, the more carefully you strip away exaggeration, the more profound the vacuum becomes. Because then you realize the real wonder is not that physics has found magic in emptiness. The wonder is that the most stripped down condition of reality still has rules rich enough to affect what can happen. There is a kind of humility in this. The vacuum does not perform for the human imagination. It does not arrange itself into simple pictures because our minds prefer stories. It remains mathematical, subtle, and resistant to easy language. Scientists can describe its effects, make predictions from it, compare those predictions with measurements, and refine the theory when needed. But they also know where the language becomes slippery. Words like restless, fluctuating, and seething are useful only if you remember that they are not photographs. They are attempts to translate a deep theory into human feeling. A child may be told that atoms are tiny solar systems, but later learns that electrons are not planets. In the same way, a listener may first hear that the vacuum is full of activity, then later learn that this activity is not a swarm of ordinary things. Understanding grows by letting the metaphor fall away when it has carried you far enough. That is what this topic asks of you. It asks you to stay awake inside the difference between wonder and distortion. The quantum vacuum is restless because a perfect, classical stillness is not available to fields in the way our everyday intuition imagines. But it is not magic because its restlessness is not lawless. It is not a miracle because it can be modeled. It is not a fantasy because its consequences connect to real experiments. It is not ordinary because it refuses to become a simple nothing. And perhaps this is why it feels so haunting. It sits right at the edge of what the mind wants emptiness to be. We want empty space to be either blank or full, either nothing or something, either silent or active. The vacuum does not obey that emotional need. It is not full in the way a room is full of furniture. It is not empty in the way a wordless page feels empty. It is a physical state with hidden depth, a condition of fields where the absence of particles still leaves a trace of quantum structure. If you listen to it correctly, it teaches a deeper lesson about reality. The universe is not obligated to match the categories your senses evolved to use. Your eyes evolved to notice surfaces, movement, color, and threat. Your hands evolved to feel contact. Your ears evolved to hear vibrations in air. None of these senses were built to understand the ground state of quantum fields. So when empty space turns out to be restless, it is not because the universe has become mystical. It is because your intuition was never designed for this level of truth. And that realization can be strangely peaceful. You do not need to fear the quantum vacuum as a monster hiding beneath matter. You do not need to worship it as a magical source. You only need to respect it as one of the deepest known layers of the physical world. A layer where silence still has structure and absence still has meaning. The restless vacuum is a reminder that reality can be active without being dramatic, powerful without being violent, mysterious without being supernatural. It shows that the universe's quietest places are not empty mistakes, but carefully ordered states whose properties are woven into the behavior of matter and light. So when you imagine the darkness between objects, do not fill it with ghosts, and do not erase it into nothing. Let it remain what it is, a quantum calm that is never perfectly frozen, a disciplined uncertainty beneath visible things, a silence whose depth cannot be reduced to magic, because it is already more astonishing as science. The vacuum is restless, yes, but its restlessness is not a trick. It is the universe obeying rules so subtle that, from far away, they almost look like wonder. Why empty space can have pressure. Pressure sounds like something that belongs to air, oceans, lungs, and storms, but one of the strangest ideas in physics is that a region with no air at all can still have a kind of pressure written into its deepest state. At first, this feels impossible because your body learned pressure through contact. You feel it when wind presses against your face, when water squeezes your ears as you dive, when the atmosphere rests quietly on your skin from every direction. In all of those cases, pressure is easy to imagine. Countless particles are moving, colliding, transferring tiny pushes to a surface. Remove the particles, and the mind expects the pressure to vanish. But physics uses the word pressure more broadly than everyday life does. Pressure is not only stuff hitting a wall. More deeply, it is a way of describing how energy and stress are distributed in a system, and how that system responds when space is stretched, squeezed, or given more room. This is where empty space becomes strange again. A vacuum has no ordinary gas inside it, but it can still have a physical state. And if that state has energy, structure, or a way of responding to changes in volume, then it can be associated with pressure. Not the familiar pressure of air in a tire, but a quieter, more abstract pressure belonging to fields and space itself. Imagine a sealed chamber with the air removed. In everyday language you call it empty, but the chamber still has boundaries. It still has size. It still contains electromagnetic field conditions, even when no light is shining through it. If you change the size of the chamber, the allowed field patterns can change too. And when the energy of a field state changes with size, physics can describe that change as pressure or stress. This does not mean the vacuum is secretly full of invisible wind. It means the vacuum is not a blank nothingness. It has rules, and those rules can make empty regions respond to geometry, boundaries, and expansion. The deeper lesson is that pressure is not always a substance. Sometimes pressure is a relationship between energy and space. A spring has pressure-like stress when compressed. A stretched membrane has tension even if it is not filled with gas. A field can have energy distributed through space, and that energy can contribute to the way space behaves. This becomes especially important in Einstein's view of the universe, where gravity is not caused only by mass in the simple, heavy object sense. Energy matters. Momentum matters. Pressure matters too. In general relativity, pressure can help shape the curvature of space-time. That may sound surprising, because on human scales, pressure seems small compared with mass. The pressure inside a room does not noticeably bend space. The pressure inside your lungs does not pull planets from their paths. But in extreme environments, inside stars, in the early universe, or in cosmic fields spread everywhere, pressure becomes part of the gravitational story. A star, for example, is held in balance partly because inward gravity is resisted by outward pressure from hot gas and radiation. Without pressure, a star would not live as a stable burning sphere for billions of years. But vacuum pressure is stranger because it is not carried by hot atoms bouncing around. It is connected to the condition of fields and space itself. One of the most important versions of this idea is negative pressure. That phrase can sound mysterious, almost like a contradiction, because we usually imagine pressure pushing outward. But negative pressure is closer to tension. Think of a stretched rubber sheet. It does not push outward like compressed air. It pulls inward along itself, resisting expansion. In cosmology, a vacuum-like energy can behave in a way that resembles this kind of tension. If a form of energy stays associated with space itself as space expands, then creating more space also creates more of that energy-filled condition. To make sense of that behavior in the equations of the universe, it appears with negative pressure. This is not a trick of words. It is one of the ways physics describes a medium whose energy density does not dilute like ordinary matter. Dust spreads out and becomes thinner. Radiation loses energy as the universe expands. But a vacuum-like energy, if it is truly tied to space itself, can remain nearly uniform. Its pressure is then not like air trying to escape a balloon. It is more like a property of the background that changes the expansion story from within. This is why pressure in empty space is not merely a laboratory curiosity. It touches the way the whole universe is understood. Still, it is important not to run too far too quickly. Saying empty space can have pressure does not mean every empty region is pushing on you in a way you can feel. It does not mean the vacuum is a hidden atmosphere. It does not mean space is a fluid in the ordinary sense. The danger of the metaphor is that it makes you imagine invisible material filling the darkness, when the more careful truth is subtler. Fields and vacuum states can possess energy and stress, and those quantities can be described with pressure-like behavior. The vacuum's pressure is not something your hand can cup. It is not a breeze. It is not a weight on your chest. It is a property of the physical state of empty space, revealed only through theory, measurement, and cosmic behavior. And perhaps that is why it is so difficult to absorb. Your senses were designed for local pressure. Skin against water, lungs against air, feet against ground. But the universe also contains pressure that belongs to radiation, fields, quantum states, and space-time. Light itself can exert radiation pressure. A beam of sunlight can push, extremely gently, on a surface. Solar sails are built around this fact. Photons carry momentum, and even though each one is tiny, together they can nudge matter. That is not vacuum pressure, but it prepares the mind for the larger idea that pressure is not always the pressure of air. It can arise anywhere energy and momentum interact with surfaces, boundaries, or expansion. In the vacuum case, the surface may be absent, or cosmic in scale, or replaced by the changing geometry of space itself. The idea becomes less like a hand pressing on a wall and more like a rule governing how the background contributes to the evolution of the system. This is the kind of concept that makes empty space feel less like emptiness and more like a hidden participant in reality. A vacuum can be calm and still have tension. It can be without matter and still have properties. It can contain no ordinary wind and still enter the equations as something with pressure. And this changes the emotional meaning of emptiness. It tells you that the absence of visible things is not the absence of physical character. A blank region of space may have a state, and that state may decide how it responds when the universe changes around it. On small scales, boundaries can reveal vacuum stresses. On cosmic scales, vacuum-like pressure may help explain why space does not behave like a simple container filled with matter. The emptiest part of reality may carry a quiet resistance or drive that only becomes visible when the universe itself is the experiment. So the next time you think of pressure, do not imagine only storms, oceans, or the weight of air. Imagine something more hidden. The way reality answers when space is given more room, the way fields keep their lower state, the way energy spread through the vacuum can behave not like a crowded gas, but like a tension woven through the background. Empty space can have pressure because pressure is not always the touch of particles. Sometimes it is the signature of a deeper condition, a silent stress in the fabric of what remains when everything familiar is gone. And that is the part worth remembering. The void does not need to be full of matter to have a voice in the universe. Sometimes its voice is pressure, quiet, invisible, almost impossible to feel, yet powerful enough to belong in the deepest description of how reality expands, balances, and holds itself together. Dark energy, the strange push, hidden in space itself. The universe is not only expanding. The truly unsettling part is that the emptiness between galaxies seems to be helping it expand faster. For most of human history, space felt like distance, a silent separation between stars, a dark ocean that objects traveled through but did not depend on. Even after scientists learned that the universe itself was growing, it was natural to expect gravity to slow that growth down. Because matter attracts matter, galaxies pull on galaxies, and the whole cosmic story seemed as if it should be a long struggle between expansion and gravity's attempt to gather everything back. But in the late 20th century, observations of distant exploding stars changed the mood of cosmology. Those supernovae were used like faraway markers, helping astronomers compare how bright they appeared with how far away they should be. And the result was startling. The expansion of the universe was not slowing down as expected. It was accelerating. Somewhere in the deep structure of reality, seemed to be pushing the cosmic scale outward. Today we call that unknown influence dark energy, but the name is not an explanation. It is a label placed over one of the largest gaps in our understanding. NASA describes dark energy as the mysterious something causing the universe's expansion to accelerate. And that humility is important, because the phrase can make it sound like we have found a substance, when in truth we have mostly measured an effect and given the mystery a name. Dark energy does not glow. It does not clump into planets. It does not behave like ordinary matter. And it does not seem to act like dark matter, which helps hold galaxies and clusters together through gravity. Dark energy is stranger because it appears connected not to places where matter gathers, but to space itself. The more the universe expands, the more empty space there is. And if dark energy is a property of space, then it does not fade away like ordinary matter spreading thinner. It remains woven through the growing background, quiet and almost uniform, like a pressure hidden in the architecture of the cosmos. This is why the idea feels so difficult. The push is not coming from a giant engine at the edge of the universe, and it is not blasting galaxies outward through space like debris from an explosion. Instead, space itself is expanding, and distant galaxies are carried apart as the distances between them grow. Dark energy is the name we give to the influence that seems to make that stretching speed up. One possible explanation is the cosmological constant, an idea connected to Einstein's equations, where empty space has a constant energy density. In that view, dark energy is not changing much over time. It is a steady property of the vacuum, gentle in any small region, but overwhelming when spread across the entire universe. This is one reason it can dominate cosmic history without being felt in your room. On Earth, in your body, inside a building, the effect is far too tiny to notice. Gravity, electromagnetism, chemistry, pressure, and motion are the things that shape daily life. But across billions of light years, when you are no longer asking what happens to a cup or a planet, but what happens to the entire fabric of expanding space, even a faint property of the vacuum can become decisive. That is the quiet terror and beauty of dark energy. It is not strong locally, but it is everywhere. A whisper repeated across all of space can become louder than a shout confined to one star. And yet, scientists are still not sure whether dark energy is truly a constant property of the vacuum or something more dynamic. It might be a field that changes slowly over cosmic time. It might point toward a modification of gravity on the largest scales. It might be connected to a deeper theory we do not yet have, one that explains why empty space has the properties it does. The Dark Energy Survey describes the accelerated expansion as something that may be caused by dark energy, or may require changes in our theory of gravity, which shows how carefully the question is still being treated. Recent measurements have made the story even more interesting. The Dark Energy Spectroscopic Instrument, or Decay, has been mapping millions of galaxies and quasars to track how cosmic expansion changed over time, and its newer results, when combined with other observations, have suggested the intriguing possibility that dark energy may evolve rather than remain perfectly constant. But this is not settled, and the word possibility matters. Science is not a horror movie where one result becomes final prophecy. It is a slow tightening of evidence, a careful comparison between different cosmic clues: supernova, galaxy clustering, baryon acoustic patterns, the cosmic microwave background, and the weak bending of light by large-scale structure. Missions like ESA's Euclid are designed to study dark energy and dark matter across enormous cosmic scales, not because the mystery is solved, but because the universe has left its fingerprints in the arrangement of galaxies and the history of expansion. If dark energy is constant, the likely long-term picture is a universe that keeps expanding faster, with distant galaxies gradually slipping beyond reach. Not because they are moving through space faster than light in a local sense, but because the space between us and them grows so much that their future light may never arrive. The night sky of the far future would become lonelier. Galaxies outside our local gravitational neighborhood would disappear beyond the cosmic horizon, leaving future observers with a much smaller visible universe. If dark energy changes with time, then the ending becomes less certain. It could weaken, altering the future expansion. It could behave in ways that point toward new physics. In more extreme speculative scenarios, dark energy-like behavior could lead to very different cosmic endings, though those are not established facts. The responsible way to say it is this: dark energy is not a daily threat, but it may be one of the main ingredients deciding the universe's long-term fate. That is what makes it so powerful. Not drama, not violence, influence. It is the kind of force that does not appear in front of you, does not interrupt your breakfast, does not shake the ground beneath your feet, but quietly changes the scale on which every galaxy lives. And perhaps the most haunting part is that dark energy returns us to the mystery of empty space. If the vacuum has energy, why is it so small compared with what some theories would naively predict? Why does it have the value that allows galaxies, stars, planets, and life to exist? Why did its influence become dominant only after the universe had already spent billions of years forming structure? These questions sit near the deepest problems in physics, because they connect the smallest theories of fields with the largest story of cosmology. Dark energy is not merely an astronomy topic. It is a bridge between the nature of the vacuum and the destiny of everything visible. It asks whether space is just the stage, or whether the stage itself has a hidden tension that shapes the final act. And once you understand that, the darkness between galaxies feels different. It is no longer just distance. It is not just the absence of stars. It may carry a quiet push written into space itself, a property so subtle that no human body can feel it, yet so vast that it can change the future of the cosmos. So when you imagine dark energy, Do not picture a glowing substance or an invisible wind blowing galaxies away. Picture something quieter and more difficult. The possibility that empty space has a built-in tendency, a faint pressure-like character, a hidden rule that becomes powerful only because the universe is unimaginably large. The strange push hidden in space itself does not make the universe feel more chaotic. It makes it feel more delicate. Every star, every galaxy, every observer exists inside an expansion whose cause is still partly unknown. And maybe that is the thought to carry with you. The future of everything may not be decided by the brightest things in the sky, but by the almost invisible property of the darkness around them, by the quiet behavior of space when nothing seems to be there. The universe is expanding because space itself can stretch. The universe is not expanding like an explosion into empty darkness. The stranger truth is that the darkness itself is changing. When people first hear that the universe is expanding, they often imagine galaxies flying outward from a central blast, like sparks thrown from a firework, racing through a giant pre-existing space. But that picture quietly places the universe inside something larger, as if there is a room outside the cosmos into which everything is spreading. Modern cosmology points to something far more difficult and far more beautiful. Space is not merely the container of the universe. Space is part of the universe, and space itself can stretch. The distance between faraway galaxies grows not only because galaxies move through space, but because the scale of space between them increases. This is why there is no single center of expansion, no special point where the Big Bang happened in the way an explosion happens at one location. The Big Bang was not matter bursting into a dark void from one spot. It was the early universe itself, hot and dense everywhere, beginning a long process of expansion everywhere. If you were in one distant galaxy, you would see most other distant galaxies moving away from you. If you were in another galaxy far across the cosmos, you would see the same thing from there. This does not mean every place is the center in a normal geographic sense. It means the expansion is built into the fabric of distances themselves. A helpful image is not a bomb, but rising dough with raisins inside it. As the dough expands, each raisin sees the other raisins getting farther away. Not because one raisin sits at the center and pushes the others outward, but because the dough between them grows. The comparison is imperfect, but it carries the key idea. The medium of separation changes. Space stretches, and the galaxies embedded in that stretching become more distant from one another on large scales. This is also why the expansion does not tear apart your body, your house, Earth, the solar system, or even galaxies themselves. Not everything expands just because the universe expands. Systems held together by stronger local forces remain bound. Atoms are held by electromagnetic interactions. Planets are held in orbits by gravity. Stars inside galaxies are bound by the galaxy's gravity. The expansion becomes important across enormous distances where galaxies are not tightly bound together. In your room, space is not noticeably swelling between the walls. Between clusters of galaxies separated by vast cosmic stretches, the expansion becomes part of the story. One of the clearest signs of this stretching is redshift. When light travels from a distant galaxy, it does not simply cross space like a message moving through a hallway that never changes. During the long journey, space itself expands, and the wavelength of that light is stretched with it. By the time the light reaches us, it has shifted toward redder wavelengths. The farther away a galaxy is, the more space has expanded during the light's journey, and the more stretched the light can become. This is not just a visual curiosity. It is one of the main ways astronomers learned that the universe is expanding. In the early 20th century, observations of galaxies showed a pattern. Distant galaxies generally appear to recede faster than nearby ones. This relationship became one of the great clues that the universe is dynamic, not static. Before that, many imagined the cosmos as eternal and unchanging on the larger scale, a grand stillness filled with stars. But the light itself carried a different message. It whispered that the stage was not fixed. The cosmic backdrop was growing. And if you follow that expansion backward in time, galaxies were closer together. The universe was denser, hotter and more compressed, until the story leads toward the early hot state we call the Big Bang. Even today, the universe carries a faint afterglow from that early era, the cosmic microwave background, cooled and stretched by expansion until ancient light became microwave radiation spread across the sky. This background is not a photograph of the first instant, but it is one of the oldest light signals we can observe, a relic from a time when the universe became transparent enough for light to travel freely. Its existence supports the idea that the cosmos has been expanding and cooling for billions of years. That is an important phrase, expanding and cooling. Expansion changes temperature. When space grows, radiation stretches, and stretched radiation loses energy. The early universe was not full of stars the way it is now. It was a hot, dense sea of particles and radiation, and only as it expanded and cooled could atoms form, then later stars, galaxies, planets, and the long chemical story that eventually produced life. So the stretching of space is not just a motion in the background, it is one of the reasons the universe has a history. Without expansion, the universe would not cool in the same way. Without cooling, matter would not settle into atoms at the right time. Without atoms, there would be no ordinary chemistry. Without chemistry, there would be no bodies to look back and ask why the stars are moving away. The stretch of space is written into the biography of everything. And yet, this stretching is still easy to misunderstand, because it does not behave like motion through ordinary space. Locally, nothing can move through space faster than light, but distant galaxies can become separated from us at rates that seem faster than light, because the space between us and them is expanding. This does not break the speed limit of physics in the usual sense, because the galaxies are not flying through their local space faster than light. The distance itself is growing. That distinction is subtle, but it matters. It is the difference between running across a road and the road itself lengthening beneath your feet. A traveler can obey every local speed rule and still find the destination becoming unreachable if the road stretches fast enough. This is why cosmology can feel almost dreamlike while remaining scientific. It asks you to let go of the idea that space is a rigid emptiness. It asks you to imagine distance as something with behavior, something measured by the geometry of the universe, something that can change with time. And when you accept that, the cosmos becomes less like a collection of objects and more like an evolving fabric of relationships. Galaxies are not simply placed in space. Their separations are part of a changing cosmic pattern. Light is not merely traveling, its journey records the history of expansion. Time is not merely passing, it is tied to a universe whose large-scale shape has been unfolding since the beginning. This does not mean space is made of rubber, or that there is a physical fabric you could touch with your hand. Those are metaphors, useful only if they do not become traps. Space-time is not cloth in a literal sense. It is the structure of distances, durations, and paths, described by physics in a way that tells matter and light how to move. When we say space stretches, we mean that the scale of distances between unbound cosmic regions increases over time. That careful wording keeps the wonder honest. It lets the idea remain astonishing without turning it into fantasy. And perhaps the most humbling part is that this expansion is not something human beings can feel directly. You do not wake up and sense the universe growing. You do not hear the distances stretch. The evidence arrives through light that has crossed ages, through patterns in galaxies, through the cooling afterglow of the early cosmos, through the patient comparison of observation and theory. The universe does not announce its expansion with noise. It leaves clues in the color of ancient light. It writes motion into distance. It turns the sky into a record of change. So when you look into space, try not to imagine a static darkness sprinkled with stars. Imagine a reality whose distances have been widening for billions of years, a cosmos where the emptiness between galaxies is not a dead gap, but part of the unfolding story. The universe is expanding because space itself can stretch, and that one quiet fact changes almost everything. Where galaxies came from, why ancient light has cooled, why the cosmos has a past, why its future is not simply a rearrangement of objects, but the continued evolution of the stage itself. The stars shine, the galaxies turn, matter gathers and dissolves. But beneath all of that, the deepest movement may be the one you cannot see. The slow growth of distance, the silent stretching of space, the universe becoming larger not by entering somewhere else, but by changing the meaning of far away from within. More empty space means a colder, lonelier universe. The universe may not end with a scream, a collision, or a final burst of fire, but with something much quieter, too much room. That is the strange emotional weight of cosmic expansion. More empty space does not simply mean more distance on a map. It means a universe where energy becomes more spread out, where radiation loses its intensity, where matter grows more isolated, and where the great engines of light slowly run out of the conditions that made them possible. In the young universe, everything was closer together, hotter, denser, more crowded with possibility. Radiation filled space with a fierce brightness. Matter had less room to hide from itself. Gas could gather more easily under gravity, collapse into the first stars, and begin the long chemical work of turning simple ingredients into heavier elements. But expansion changes the mood of reality. As space grows, the average density of matter drops. The same amount of matter becomes distributed across a larger cosmic volume, like a handful of smoke thinning in an enormous dark hall. Radiation cools as its wavelengths are stretched by the growing universe. The ancient afterglow of the early cosmos, once hot enough to belong to a universe before atoms could settle, has faded into the cold microwave background we detect today, only a few degrees above absolute zero. And it will keep fading, not because it disappears all at once, but because expansion gently stretches it into weaker and weaker forms. This is one of the key reasons more empty space means a colder universe. Light itself is tired by distance when the distance grows beneath it. Its energy thins, its temperature falls, its presence becomes softer, older, harder to notice. But the cooling is not only about radiation, it is also about structure. Stars are born from gas, and gas is not infinite. Over cosmic history, galaxies turn their gas into stars. Stars return some of it through winds and explosions, and new generations form from what remains. Yet this cycle is not perfectly renewable. Some gas becomes locked into long-lived stars, stellar remnants, planets, or hot diffuse regions where it cannot easily collapse again. Some is pushed out by energetic events. Some becomes too thin, too warm, or too scattered to make stars efficiently. Observations show that the universe's rate of star formation was much higher in the past than it is today. The cosmos has not stopped making stars, but its great star-making era has been declining for billions of years. That fact gives the future a quiet sadness. The universe is not running out of space. It is running out of the right kinds of crowdedness. A star needs gravity to gather gas tightly enough for pressure and temperature to rise until fusion begins. But as the universe becomes more spacious and as usable gas becomes less available, new stars become rarer. The night sky may still contain light for unimaginably long ages, especially because small red dwarf stars can burn slowly for trillions of years, far longer than the sun. But even those patient stars are not eternal. The future is not a sudden darkness, but a long dimming. Massive stars die first, quickly and violently. Sun-like stars age more slowly, swelling, shedding layers, and leaving behind white dwarfs. The smallest stars take the longest, spending their fuel with extraordinary restraint. Eventually, in the far future, if our current understanding is broadly correct, the universe becomes dominated less by shining stars and more by remnants. White dwarfs cooling toward black dwarfs, neutron stars, black holes, and cold planets drifting through an expanding dark. Even black dwarfs are still hypothetical because the universe is not old enough for any white dwarf to have cooled that far yet. That detail matters because it reminds us that cosmic endings are not things we have watched happen. They are careful extensions of physical laws into timescales almost impossible to feel. And on those timescales, loneliness becomes a physical condition, not just a mood. Today, galaxies live in groups, clusters, filaments, and neighborhoods of gravity. They interact, they merge, they disturb one another. Gas is pulled, compressed, heated, and reshaped. But as expansion continues on the larger scales, regions not bound together become increasingly separated. Bound systems like galaxies and galaxy groups can remain together, but the wider universe becomes less connected in practice. The emptiness between large structures grows, encounters become rarer. Fresh material becomes harder to gather. The cosmos shifts from a rich web of exchange toward isolated islands of memory. And because temperature is connected to the movement and distribution of energy, the long-term picture becomes colder as usable energy becomes less concentrated. This is related to the idea of heat death, but the phrase can be misleading if imagined as fire. Heat death is not everything burning. It is almost the opposite. It is a future where energy differences have been smoothed out so much that useful work becomes harder and harder to extract. Engines need contrast. Hot and cold, dense and thin, high energy and low energy, one place different from another. Life itself depends on gradients, on flows, on energy moving from one form to another. Stars shine because gravity creates extreme conditions and fusion releases energy. Planets can host weather, oceans, and biology because energy arrives unevenly and is processed through matter. But a universe with more and more empty space, fewer new stars, colder radiation, and more diluted matter slowly loses the sharp contrasts that make activity abundant. It does not become nothing. It becomes quiet. It becomes even. It becomes a vast archive of what once burned. This is why empty space feels so important to the future. It is not merely the background into which the universe expands. It is the growing condition that changes what kinds of events remain likely. More space means fewer meetings between unbound things. More space means ancient light becomes weaker. More space means the raw materials for new brightness become harder to collect. More space means the universe becomes less like a crowded workshop and more like a cathedral after the candles have burned low, still standing, still real, but filled with a silence that has outlived the choir. And yet, this should not be told as simple despair. The fact that the universe can grow cold and lonely is also the reason it had time to become complex. If everything had remained too dense and hot, atoms could not have formed in a stable way. If matter had never spread out, stars and galaxies might not have separated into structures where chemistry could unfold. Emptiness gives reality room to become. The same expansion that cools the cosmic background also allowed the universe to move from its early fire into transparency, then into stars, then into planets, then into minds capable of imagining the far future. So empty space is both the gift and the cost. It gives structure room to appear, but eventually gives everything so much room that connection becomes rare. It allows the first lights to shine, then slowly carries the last lights into deeper distance. And perhaps that is the most haunting balance in the story. The universe becomes beautiful because it expands, and it becomes lonely for the same reason. More empty space does not attack the cosmos. It simply changes the conditions, gently and relentlessly, until heat thins, stars become fewer, and the great conversations between matter grow quiet. So when you look at the dark between stars, do not think of it only as emptiness. Think of it as the future arriving early, a preview of the long cooling that waits at the edge of time. Every stretch of space is a little more room for light to fade, for matter to drift, for the universe to become less crowded with fire and more filled with memory. And still, here you are, living in the bright middle age of things, when stars still burn, galaxies still glow, and the cold loneliness of the far future has not yet taken the sky. The universe may one day become colder because it has too much space, but for now, that same space holds every light you have ever seen and gives your brief awareness a place to wonder before the silence grows. Distant galaxies are slowly disappearing beyond reach. There are galaxies in the sky whose light is still reaching us, yet whose future may already be permanently lost to us. That is one of the quietest and most haunting truths in cosmology. The universe does not have to destroy something to take it away. It only has to keep expanding. When you look at a deep image of the cosmos, filled with thousands of galaxies scattered like faint embers across blackness, it feels as if you are seeing a map of places that could, at least in imagination, be reached one day by a patient enough civilization. They are there, they shine, their light arrives. They belong to the same universe. But belonging to the same universe does not mean remaining connected forever, because space is expanding, and because that expansion appears to be accelerating. Many distant galaxies are slowly slipping beyond a cosmic boundary. Not a wall made of matter, not an edge you could crash into, but a limit created by the growth of space itself. The important idea is not that those galaxies suddenly vanish from existence. They do not fall off the universe. They do not blink out like lamps being switched off. From their own point of view, they remain surrounded by stars, gas, dust, planets, and their own local sky. But from our point of view, their future signals become unreachable. Light they emitted long ago can still be traveling toward us now, like ancient messages crossing a sea that was smaller when the journey began. But light they emit far enough in the future may never arrive, because the space between us and them will stretch faster than the light can make progress across the growing distance. This is the idea of a cosmic event horizon. Not the same as a black hole's event horizon, but a limit on what can ever affect us or be seen by us in the future. It is a horizon made of time, distance, and expansion, and it changes the emotional meaning of the night sky. Some of the galaxies you see are not invitations. They are farewells. Their light is not a promise that connection remains possible forever. It is a memory from a universe that was once more connected than it will be. This is different from the observable universe, which is the region from which light has had time to reach us since the early universe became transparent. The observable universe is already enormous, but it is not the whole universe. Beyond it may lie far more space, perhaps infinitely more, filled with regions whose light has not reached us and may never reach us. The cosmic event horizon is even more subtle. It concerns what can ever reach us from now onward, given the universe's future expansion. A galaxy can be visible today and still be beyond our future reach in the sense that new light from it, emitted after a certain time, will never get here. This is why cosmic disappearance is not a sudden blackout. It is a long fading. As galaxies recede with the expansion of space, their light becomes stretched toward longer and longer wavelengths. Visible light shifts toward infrared, then microwave, then radio, becoming harder to detect, weaker in energy, thinner in information. Their clocks would appear to slow from our viewpoint, their changes arriving more and more delayed, as if the universe were gradually turning down the volume on their existence. For a very long time, powerful telescopes could still collect their old light. But eventually, for distant enough galaxies, the stream becomes so redshifted and diluted that they fade into practical invisibility. The galaxies are not gone in themselves, they are gone from relationship. And that distinction matters, because physics often teaches that separation is not only about where something is, but whether it can still exchange signals with you. A thing can exist and still be unreachable. A civilization could live in a galaxy beyond our future horizon, build telescopes, ask the same questions, and yet no message from us would ever arrive after the separation becomes permanent. No greeting, no warning, no proof that we were here. Cosmic expansion turns parts of the universe into sealed histories. On the largest scales, the future becomes a collection of islands that can no longer speak to one another. Our own island will be the local group, the family of galaxies gravitationally bound together, including the Milky Way and Andromeda. These galaxies are not being pulled apart by cosmic expansion because their mutual gravity is strong enough to keep them bound. In fact, the Milky Way and Andromeda are expected to merge in the far future, forming a larger galaxy. But beyond our gravitational neighborhood, the wider cosmic web will continue to recede. Galaxy clusters not bound to us will drift beyond reach. The great structure that looks so rich and connected today will become, for future observers, increasingly hidden. If intelligent beings exist in our distant future, living around long-lived stars after many billions, or even trillions of years, they may look into the sky and see a much smaller universe. The evidence of cosmic expansion could become harder to discover. The cosmic microwave background will be stretched into wavelengths so long and cold that detecting it may become nearly impossible. Distant galaxies that helped us understand the Big Bang and the expanding cosmos may have faded beyond observational reach. Future astronomers might see only their local merged galaxy against a dark, empty-looking background and think the universe is small, static, and lonely. In that sense, cosmology has an error. We live at a privileged time, not because we are central, but because the universe is still young enough and bright enough for its history to be visible. The sky still contains evidence. The ancient light has not yet faded beyond detection. The galaxies are still close enough, in cosmic terms, to tell us that the universe is expanding. The universe is still willing to reveal itself, but it will not do so forever. This gives every deep field image a strange tenderness. Those faint smudges are not only distant places, they are disappearing chapters of the cosmic library. We are receiving pages from them now, but the library is being carried down endless corridors, and eventually some shelves will pass beyond any door we can open. The process is not violent. That is what makes it feel so profound. A supernova dies loudly. A black hole hides dramatically, but the cosmic horizon takes things away without drama. It stretches the silence until communication fails. It turns visibility into memory. It teaches that the universe's future is not only about what exists, but about what remains knowable. And this raises a deeper question. How much of reality is already beyond us? Not because it is unreal, but because no signal can cross the distance in time. Human beings often confuse existence with access. If we can see it, measure it, touch it, or receive information from it, we call it part of our world. But cosmology humbles that instinct. There may be vast regions forever outside our observation. There may be galaxies whose stories are complete and rich, yet absent from our sky. There may be events happening right now that will never become part of our history because their light will never reach us. The universe is larger than communication. Reality is bigger than evidence available to one location. And so the disappearance of distant galaxies is not merely a future loss. It is a lesson about the limits of knowing. The cosmic horizon is the universe reminding us that there are truths no telescope can eventually recover if expansion carries them too far. This does not make science weaker. It makes the act of observing more precious. Every photon that arrives from a distant galaxy is a messenger that succeeded before the door closed. Every redshift measured, every galaxy mapped, every ancient signal captured is part of a race against cosmic isolation. Not a race we can win by stopping expansion, but a race to understand as much as possible while the universe is still readable. So when you see a distant galaxy in an image, try to imagine both truths at once. It is there, and it is leaving. It is visible, and its future may be unreachable. It shines, but the path for its later light may already be closing. The galaxy is not disappearing because it failed, or because darkness swallowed it, or because space is cruel in any human sense. It is disappearing beyond reach because the universe is dynamic, because distance can grow, because horizons are not only found around black holes, but woven into cosmology itself. And perhaps that is the soft sadness hidden in the expanding universe. The sky we see is not permanent. It is a temporary conversation between here and elsewhere, between now and long ago, between light that made it and light that never will. Distant galaxies are slowly disappearing beyond reach, and in their fading, they leave us with one clear thought. The cosmos is not only a place full of things, but a place where access changes with time. The universe does not need to erase its wonders to hide them. It only needs to keep stretching the silence between us. The void may decide the final fate of everything. The final fate of the universe may not be decided by the stars that shine, but by the empty space that remains after their light has faded. That is a difficult idea to accept, because we are used to thinking of endings as dramatic events. A final explosion, a collapse, a fire, a collision, a last visible moment when something breaks. But the cosmos may be governed by a quieter judge. The void, The vast emptiness between structures may carry the properties that determine whether everything drifts into stillness, tears apart, turns back inward, or settles into an eternal cold expansion. In the early universe, matter and radiation were dominant characters in the story. Their density, heat, motion, and gravity shaped what could form. Matter gathered into galaxies, gas collapsed into stars, stars built elements. Gravity sculpted structure from the almost smooth young cosmos. But as the universe expanded, matter became more diluted, radiation cooled, and something associated with empty space became more important in the balance of the whole. This is where the fate of everything begins to feel less like a story about objects and more like a story about the background itself. If the energy of empty space stays constant as the universe grows, then it acts almost like a permanent influence spread through the cosmos. Ordinary matter thins out as space expands because the same matter is spread over a larger volume. Radiation thins and weakens even faster because its wavelengths stretch as the universe grows. But a vacuum-like energy, if it truly belongs to space itself, does not fade in the same simple way. As more space appears, the same kind of vacuum condition appears with it. That means the emptiest ingredient can eventually become the most important one, not by growing louder locally, but by outlasting everything else. In the leading picture used by cosmologists today, the universe continues expanding forever, and the future becomes a long, slow movement toward what is often called heat death, not an explosion of heat, but the fading of usable differences. Stars exhaust their fuel, new star formation declines, stellar remnants cool, black holes remain for immense stretches of time. Then, according to our best understanding of quantum effects near horizons, may very slowly lose energy through Hawking radiation over unimaginable ages. Eventually, the universe becomes sparse, cold, and quiet, with matter either locked into remnants, dispersed, or decayed, depending on physics we still do not fully know. In that future, the void is not a background to life, it is the dominant condition. But this is only one possible ending, because the final fate depends on what empty space really is. If dark energy is truly constant, the universe may approach an endless accelerated expansion, where distances grow, horizons remain, and the reachable cosmos becomes a smaller and smaller island of gravitationally bound matter surrounded by inaccessible space. But if the dark energy changes over time, the ending could be different. If its influence weakens, expansion might slow, and the universe's future could become less lonely than the simplest model suggests. If its behavior becomes stronger in a certain extreme way, a speculative scenario called the Big Rip could occur, where expansion eventually becomes so intense that it overcomes not only clusters and galaxies, but stars, planets, and even atomic structures. This is not the favored everyday expectation, and it should not be told as prophecy. It is a theoretical possibility that shows how deeply the cosmic ending depends on the hidden behavior of the vacuum-like component. There is also the older possibility of a big crunch, where the expansion eventually reverses and the universe collapses back into a hot, dense state. Current evidence does not point strongly toward that ending in the simplest models, because expansion appears to be accelerating. But the idea remains important historically and conceptually, because it reminds us that the universe's fate is not determined by expansion alone. It is determined by the balance between expansion, gravity, the density of matter, the shape of space, and the properties of whatever fills the vacuum. There are even more speculative possibilities. A big bounce, where a collapsing universe might avoid a final singularity and transition into a new expanding phase, or a changing vacuum state that could alter the laws of physics in the far future. None of these should be presented as certainties. They are not bedtime monsters hiding behind the stars. They are scientific attempts to ask what the universe is allowed to become if the deepest properties of space are different from what we assume. This is why the void may decide the final fate of everything. The important question is not only how much matter exists, but what kind of emptiness surrounds it. Does empty space have a fixed energy? Does that energy remain unchanged forever? Is it connected to a field that slowly evolves? Is it a temporary state? Does gravity respond to it exactly as our current theories say? These questions sound abstract, but their consequences are enormous. Change the answer slightly, and the far future changes with it. A constant vacuum points toward endless dilution and cold isolation. A weakening vacuum could allow a different cosmic rhythm. A strengthening vacuum could create a more violent separation. A collapsing possibility could turn expansion into reversal. The fate of stars, galaxies, black holes, time, and any future observers may rest on a property of space too subtle for human senses to notice. And perhaps that is the most humbling part. The universe may be governed at the end not by the things that look powerful now, but by the quietest condition underneath them. The brightest stars are temporary. The grandest galaxies are temporary. Even black holes, the most durable objects we know, may not be eternal. But the vacuum, or whatever deeper state lies beneath what we call vacuum, may remain as the final arena in which all endings unfold. To ask about the end of the universe is therefore to ask about the nature of emptiness. Not emptiness as a blank absence, but emptiness as a physical state with pressure, energy, stability, and possibility. It is strange to realize that the final chapter of reality may already be written into the spaces between things, not as a fixed script we can read, but as a set of hidden tendencies. The void does not need to move like a creature. It does not need to attack matter or swallow light. Its power comes from being everywhere and from lasting longer than the structures built inside it. In the far future, when the last ordinary stars have dimmed and the sky has lost its crowded depth, the universe may reveal what was true all along. The visible world was a temporary pattern raised on a much deeper background. The final question will not be what the stars wanted or what galaxies became, but what empty space allowed. So when you hear the word void, do not imagine a useless darkness around the real universe. Imagine the quiet condition that may decide whether reality expands forever, cools into silence, tears itself apart, turns back inward, or changes into something no current mind can fully predict. The void may decide the final fate of everything, because it is not merely what remains after the story ends. It may be the page on which the ending is written, false vacuum. What if space is only temporarily stable? What if the universe is not resting on the deepest floor of reality, but on a higher ledge that only feels like the ground because it has held us for so long? This is the strange idea behind the false vacuum, and it may be one of the most delicate concepts in modern physics, because it sounds terrifying when rushed, but becomes more meaningful when handled carefully. To understand it, imagine a landscape with valleys of different depths. A ball sitting in one valley can seem perfectly stable if the walls around it are high enough. It does not roll, it does not shake, it does not look unsafe. If you lived your entire life beside that ball, you might call its valley the natural resting place. But if somewhere else in the landscape there is an even deeper valley, then the ball is not in the true lowest state. It is only in a local resting place, stable for now, but not the deepest possible one. In physics, a vacuum is not simply empty space in the everyday sense. It is the state of the fields that fill reality when they are as settled as they can be. A true vacuum would be the lowest possible state, the deepest valley. A false vacuum would be a state that looks stable, behaves stable, and may last for an unimaginably long time, while still not being the final deepest state nature could take. This does not mean the universe is secretly cracking under your feet tonight. It does not mean disaster is expected in daily life. It means that the stability of space itself is a scientific question, not something we get to assume just because the world feels solid. The reason physicists take this seriously is connected to the Higgs field, the field associated with the Higgs boson discovered at CERN in 2012, and with the way fundamental particles acquire mass in the Standard Model. Based on the measured values of the Higgs boson and the top quark, some calculations suggest that our vacuum may be metastable, not obviously unstable, not falling apart, but perhaps not the absolute lowest energy state either. The important word is may. The conclusion depends on extremely precise measurements and on assuming that no unknown physics changes the picture at higher energies. The standard model is powerful but not necessarily complete. It does not include a full quantum theory of gravity. It does not explain dark matter. It does not answer every question about the early universe. So when someone says the universe might be in a false vacuum, the honest meaning is not, we know the universe will decay. The honest meaning is, within certain calculations using known physics, the vacuum appears possibly long-lived rather than guaranteed to be the deepest possible state. And long-lived here does not mean long in a human sense. It can mean timescales so vast that the age of the universe is almost nothing compared with them. A metastable vacuum can be like a diamond, not the absolute most stable form of carbon under ordinary conditions, yet stable enough that it does not suddenly become graphite in your hand. Stability in physics is not always a simple yes or no. Sometimes it is a question of barriers, probabilities, and time. In the false vacuum picture, the universe could remain in its current state because an energy barrier separates it from the deeper, true vacuum. Classical intuition would say the field cannot cross that barrier unless it has enough energy to climb over it. But quantum physics allows a more subtle possibility called tunneling, where a system has a tiny chance of passing through a barrier rather than climbing over it. If vacuum decay ever occurred, it would begin with a small region of space transitioning into the lower energy vacuum state, forming what physicists call a bubble of true vacuum. If that bubble were energetically favored, it could expand outward, converting the surrounding false vacuum as it went. This is where the idea becomes famous for being frightening, because inside such a bubble, the values of fields could be different. And if the fields are different, the properties of particles and forces could be different too. Atoms might not hold together the same way. Chemistry might fail. Matter as we know it might not be able to exist. But this is exactly where the narration must stay grounded. Vacuum decay is not a storm moving through ordinary space. It is not a wave of fire. It is not a monster traveling between stars. It is a theoretical transition in the state of the fields themselves. If it happened, it would not be something you could see approaching from far away and prepare for, because the change would propagate at nearly the speed of light. But again, if is the key word. The fact that a process is allowed in a theory does not mean it is likely on any meaningful timescale. Radioactive atoms can decay randomly, yet some isotopes have half-lives far longer than the current age of the universe. A possible quantum transition can be so suppressed that for all practical purposes, the universe remains safe for durations beyond imagination. Current scientific discussions of vacuum metastability generally point toward extraordinary longevity if the standard model picture is correct, and if no new physics intervenes in a destabilizing way. So this idea should not be used as cheap fear. It should be used as a doorway into humility. It tells us that empty space may have a kind of hidden condition, and that the rules of our universe may depend on that condition staying as it is. The mass of particles, the structure of atoms, the behavior of forces, the possibility of chemistry, the existence of stars, and the stability of matter may all be connected to the vacuum state beneath them. That is the real awe. Not that the universe is doomed, but that what we call normal reality may be balanced on a field configuration so deep we only partly understand it. Think of how ordinary the world feels from the inside. You wake up, touch a wall, drink water, hear a voice, watch sunlight cross the floor. Nothing about that experience suggests that the laws allowing it may depend on the universe occupying one particular valley in a hidden energy landscape. But physics keeps revealing that the familiar is not always fundamental. A solid table is not solid in the way it feels. A particle is not a tiny bead in the way imagination wants. Empty space is not nothing. And now, with the false vacuum idea, even stability itself becomes more subtle. Maybe the vacuum is truly stable, the deepest possible state, and reality is resting on the final floor. Maybe it is metastable, settled into a valley that will last so long that the difference has no practical consequence for life, stars, or any future civilization we can imagine. Maybe unknown physics changes the entire question, making the vacuum safer, stranger, or structured in a way our current theories cannot yet see. All of these possibilities remind us that science is not only about certainty, it is also about identifying the right uncertainty. The false vacuum is not a prophecy, it is a question written into the foundation of the universe. Is the space around us final, or only temporarily settled? And the emotional power of that question comes from the fact that the vacuum is everywhere. It is not hidden in one distant corner. It is not locked inside a black hole. It is the condition underlying every room, every galaxy, every atom, every breath. If its state matters, then it matters universally. Yet that universality should make us thoughtful, not panicked. The universe has already existed for about 13.8 billion years in its current broad form. Stars have formed, galaxies have grown, planets have cooled, life has appeared. Minds have emerged that can ask whether the ground state of reality is permanent. Whatever the vacuum is doing, it has allowed an enormous cosmic history to unfold. That is not a reason for fear, it is a reason for reverence. The false vacuum idea makes the universe feel less like a finished object and more like a state. Something stable enough to hold galaxies, but mysterious enough to keep physicists awake in the best possible way. So when you hear false vacuum, do not imagine a lie, as if space is pretending to be real. Imagine a possible plateau in the hidden landscape of fields, a place where reality can rest for ages, perhaps forever for all practical purposes. While the deeper mathematics asks whether another valley exists below. The danger, if there is one, is not a creature in the dark. It is the realization that the dark has structure, that stability has depth, and that the emptiest thing around you may be carrying the conditions that allow everything else to exist. Space may be only temporarily stable, or it may not be, but the question itself changes how the universe feels. It tells you that the ground beneath all things is not ordinary ground at all. It is a quiet agreement between fields, energy, and time, and for now, that agreement holds. Vacuum decay. The most terrifying idea in modern physics. The most frightening end of the universe is not one where something enters space, but one where space itself changes what it means to exist. Vacuum decay sounds like science fiction because the words feel too simple for the idea they carry. The vacuum decays. Not a star, not a planet, not a galaxy, not matter in the ordinary sense, but the underlying state of the fields that define the rules matter depends on. If false vacuum is the possibility that our universe may be resting in a stable-looking but not absolutely final state, vacuum decay is the hypothetical transition from that state into a deeper one. And the reason it feels so terrifying is not because it would be loud, fiery, or monstrous. It is terrifying because it would not be an attack inside the universe. It would be a change in the universe's operating conditions. Imagine living your whole life inside a house where every wall, floor, and doorway depends on one hidden agreement beneath the foundation. Then imagine that agreement changing, not by cracking the walls one at a time, but by redefining what a wall is allowed to be. That is closer to the fear of vacuum decay. In ordinary disasters, the rules remain the same. A volcano erupts, but chemistry still works. A star explodes, but atoms still have their familiar structure. A black hole forms, but gravity, light, and matter still obey the same laws around it. Vacuum decay is different in concept, because the transition would involve the vacuum state itself changing. And if the vacuum state changed, the values of fundamental fields could change with it. The masses of particles, the strengths of forces, the stability of atoms, the behavior of chemistry, all of these may depend on the vacuum we inhabit. So the danger is not that objects would be smashed by a conventional blast. The deeper danger is that the rules allowing objects to exist as they do might no longer apply inside the new vacuum. This is why physicists describe the idea with a bubble. Somewhere, through a quantum process, a tiny region of space could transition into a lower energy vacuum state. If that new state were truly favored, the region could expand outward, converting neighboring space as it moved. The bubble wall would not be like a wall of smoke or flame. It would be the boundary between one state of reality and another. Outside it, the universe would remain as we know it. Inside it, the field values could be different, and that could make familiar matter impossible. The terrifying elegance of the idea is that it does not require a villain. It does not require a cosmic weapon. It does not require a civilization making a mistake in a laboratory. Vacuum decay, if allowed and if not fantastically suppressed, would be a natural quantum transition. The universe moving from a higher energy state to a lower one, like a system finally finding a deeper resting condition. But this is where the fear must be balanced with honesty. The fact that a process can be imagined within a theory does not mean it is likely on any timescale that matters to us. Our universe has already lasted billions of years. It has survived the violent early cosmos, the birth and death of countless stars, the formation of galaxies, and particle collisions far more energetic than anything humans create on Earth. Cosmic rays strike the atmosphere with energies beyond our accelerators, and they have been doing so for ages. If ordinary high-energy events could easily trigger catastrophic vacuum decay, the universe would probably not still look the way it does. This is one reason serious physicists do not treat vacuum decay as a practical daily threat. It is not something to fear while going to sleep. It is not a reason to panic about particle physics experiments. It is an extreme theoretical possibility tied to the deepest question of whether the vacuum is absolutely stable or merely metastable for an unimaginably long time. And unimaginably long here is not casual language. In many discussions, if our vacuum is metastable, its expected lifetime could be vastly longer than the current age of the universe. That means vacuum decay may be one of the most terrifying ideas emotionally, while also being one of the least relevant dangers practically. Its power is philosophical and scientific more than personal. It reveals that the foundation of reality may have a hidden depth we cannot feel. It asks whether the universe's stability is a permanent truth or an extraordinarily durable condition. It shows that what looks like empty space may contain the fate of matter, not by doing anything visible, but by being the state on which every visible thing depends. And this is why the idea belongs in modern physics rather than mythology. It comes from thinking seriously about fields, energy states, quantum tunneling, and the shape of the potential landscape that fields may occupy. If a field is sitting in a state that is not the lowest possible one, a transition to a lower state may be allowed in principle, but the probability can be so tiny that the state is effectively stable for cosmic durations. This is not unusual in physics. Many systems can remain in a metastable condition because there is a barrier separating where they are from where they could eventually go. A supercooled liquid can remain liquid below its normal freezing point until a small disturbance lets crystallization begin. A soap bubble can hold its shape until conditions change. These comparisons are not perfect because the vacuum is not a liquid or a bubble of soap, but they help the mind approach the idea. Stability can be real without being absolute. Something can last long enough to build worlds and still not be the deepest possible state in theory. What makes vacuum decay so much more profound than ordinary metastability is the scale of what would change. If water freezes, the water changes. If a magnet flips, the magnet changes. If the vacuum decays, the background conditions for everything may change. The new vacuum would not merely rearrange matter, it could redefine the relationships that make matter meaningful. A proton, an electron, a photon, an atom, a molecule. These words only make sense inside a universe whose fields have certain properties. Change those properties enough, and the dictionary of existence changes. This is the part that should make the listener quiet, not because doom is near, but because reality suddenly feels conditional. The familiar world becomes less like an eternal machine and more like a long-held balance. Your body, your memories, the warmth of a room, the light from a lamp, the stability of the ground beneath you. All of it depends on the vacuum remaining in the state that allows those structures to persist. And yet, there is comfort hidden inside the same idea. If the vacuum can be studied, if its stability can be estimated, if its risks can be framed in terms of theory and observation, then fear becomes inquiry. The terrifying thought becomes a scientific question. We are not helpless before a superstition. We are trying to understand the deepest layer of the physical world, measurements of the Higgs boson and the top quark matter, because they help shape our picture of vacuum stability. Future physics may reveal new particles or symmetries that change the conclusion entirely. A deeper theory of quantum gravity may transform the question in ways we cannot yet see. So vacuum decay is not a final answer. It is a frontier. It is a signpost pointing toward what we still do not know about the vacuum, the Higgs field, the early universe, and the hidden architecture beneath the standard model. Calling it the most terrifying idea in modern physics makes sense only if we understand what kind of terror it is. It is not the fear of something hunting us. It is the awe of realizing that the quietest thing in the universe may be more fundamental than the brightest. It is the unease of discovering that space is not merely a place where events happen, but a state whose stability makes events possible. It is the recognition that the end of everything, in some theoretical scenario, would not come as fire from the sky, but as a new definition of sky, fire, and everything. And still, for you, here, now, the right response is not panic. The right response is wonder sharpened by honesty. The vacuum around you has held long enough for stars to forge elements, for planets to form, for life to rise, for minds to name the possibility of its decay. Whatever its ultimate nature, it has been stable enough to carry an immense cosmic story. So when you hear the phrase vacuum decay, let it disturb you in the right way. Not as a prediction, not as a warning for tomorrow, but as a reminder that the universe may be resting on a foundation deeper than matter, older than stars, and stranger than emptiness. The most terrifying idea in modern physics is not that something might destroy the universe from within. It is that the universe may depend every moment on the silent stability of what we once called nothing. Why we could never see vacuum decay coming. The most unsettling part of vacuum decay is not only what it might do, but that no warning could arrive before it. In almost every disaster you can imagine, the universe gives some kind of signal. A storm gathers clouds before it breaks. A volcano trembles before it erupts. A star approaching the end of its life changes, brightens, sheds layers, and leaves clues in its spectrum. Even a black hole, invisible by itself, can announce its presence through the motion of nearby matter, through radiation from falling gas, through the way it bends light around it. But vacuum decay, if it were possible in the form physicists describe, would be different in the deepest way. It would not be a wave traveling through space that could send a message ahead of itself. It would not be a visible front of fire moving slowly enough for telescopes to notice. It would not be a cosmic storm with thunder before lightning. The change would be the message. If a bubble of lower energy vacuum formed somewhere, the boundary of that bubble would expand outward at nearly the speed of light, or so close to it that no ordinary warning could outrun it. And because nothing carrying information can travel faster than light, no signal from the approaching boundary could reach you before the boundary itself did. You would not see it coming across the sky. You would not receive a strange red glow from distant space and have time to ask what it meant. The first moment it could affect you would also be the moment the familiar rules of matter, light, and atoms were no longer guaranteed to remain familiar. This is what makes the idea so quiet and so absolute. Not that it is expected, not that it is likely, not that it belongs among daily fears, but that if such a transition happened far away and expanded toward us, causality itself would prevent an early warning. The universe has a speed limit for information. Light, gravity waves, radio signals. Any message that says something has happened over there must cross the distance between there and here. But if the wall of changed vacuum is moving at the same cosmic speed limit, the announcement and the event arrive together. It is like trying to hear the sound of a door closing, when the closing of the door is already the thing that removes the room you are standing in. This does not mean vacuum decay is hunting us from somewhere. It does not mean there is already a bubble racing across the universe. It means that the hypothetical process, by its nature, would be hidden until arrival, because the laws of relativity forbid faster than light warning. And that is a different kind of fear from the fear of impact or explosion. It is the fear of a horizon, a boundary beyond which knowledge cannot come early. You can understand this by thinking about distant stars. When a star explodes in a galaxy millions of light years away, we do not see the explosion when it happens there. We see it when the light reaches us. The event and our knowledge of the event are separated by the time light needs to travel. If something from that explosion could travel slower than light, we might see the light first and know it was coming. But if the destructive influence itself traveled at the speed of light, then the warning light and the destructive front would arrive together. There would be no early message. Vacuum decay takes that logic to an even more fundamental level, because the front is not ordinary debris. It is not matter flying outward. It is a transition in the state of space itself. Inside the new vacuum, the values of fields might be different, and therefore the properties of particles could be different. Outside, our familiar vacuum remains. The boundary between the two is the dividing line between one set of physical conditions and another. If that boundary reached us, there would be no separate messenger ahead of it, because any messenger would have to move faster than the boundary to warn us, and the universe does not allow that. This is why telescopes would not save us in the simple vacuum decay scenario. Telescopes work by receiving light. They can only show us events after light from those events has reached us. If the event itself expands at the same speed as its first possible signal, then observation cannot become preparation. The sky could look normal until the final instant because normal is all the information that has had time to arrive. In a deep sense, the universe is always showing you its past. The sun you see is already minutes old. The nearest stars are years old. Distant galaxies are millions or billions of years old. Looking outward is looking backward. If a vacuum decay bubble formed beyond the region whose updated information can reach us now, we would not know. Not because our instruments are weak, but because the information is not here yet. Science cannot detect a signal that causality has not delivered. That is an important distinction. Ignorance from poor tools can improve. Ignorance from the structure of space-time is built into the universe. And yet, this should be held gently, not used to create panic. Many things are unknowable in principle, but not all unknowable things are meaningful threats. The possible lifetime of a metastable vacuum, if our vacuum is metastable at all, may be so enormous that the risk across any human timescale is effectively absent. The universe has already survived for billions of years. It has contained high-energy cosmic events far beyond anything humans can create. If vacuum decay were easy to trigger or common on short timescales, the long cosmic history around us would be difficult to explain. So the fact that we could never see it coming does not mean it is coming. It means that some hypothetical events, if they occur, are not the kind of events that allow spectators. This is what makes the topic worth teaching carefully. It is not a warning siren. It is a lesson about the limits of prediction. Human beings often believe fear comes from knowing that something bad will happen. But sometimes the deeper discomfort comes from knowing that reality has categories of change that would not ask permission from observation. Vacuum decay belongs to that category in theory. It would not be forecast like weather. It would not be tracked like an asteroid. It would not be seen on a horizon like a storm front. The horizon would be the event itself, and that teaches something profound about physics. Even perfect knowledge of the laws may not give perfect access to the future, because information must still travel. A civilization could build telescopes the size of planets, detectors colder than interstellar night, computers capable of modeling fields with breathtaking detail, and still be unable to receive a signal before a light speed boundary arrived. The limitation would not be intelligence, it would be the architecture of causality. This makes vacuum decay feel almost like a cosmic version of silence. Not silence because nothing is happening, but silence because no message can come ahead of the change. Still, there is a strange peace hidden inside that. If something cannot be predicted, cannot be prevented, cannot be prepared for, and is not expected on any practical timescale, then it is not a useful fear to carry through ordinary life. You do not become wiser by lying awake imagining a boundary no one could see. You become wiser by understanding what the idea reveals. that empty space may have a state, that this state may be connected to the stability of all matter, that relativity limits warning, and that the universe is not obligated to make every possible danger visible before it arrives. In daily life, the vacuum remains steady, atoms hold, light travels, chemistry works, stars continue burning. The floor beneath you is not waiting for a sign from the sky. The right response is not dread but humility. The idea of unseen vacuum decay shows that some of the deepest questions in physics are not only about what exists, but about what can be known before it reaches us. It reminds you that observation is not a throne above reality. It is a relationship with reality, limited by distance, light, and time. So when you hear that we could never see vacuum decay coming, let the sentence land in the right place, not as a prediction of doom, but as a window into how strange the universe becomes when the foundation itself is part of the story. A star can warn you with light, a planet can warn you with motion, a storm can warn you with pressure and wind. But if the vacuum itself changed, there might be no separate warning, because the rules that carry warnings would be arriving with the change. That is why this idea feels so haunting. The most invisible thing in the universe would remain invisible until it was no longer the same universe for you at all. And perhaps the final lesson is this: the silence between stars is not only a place where secrets hide, it is also a place where the speed of knowledge has a limit. The vacuum may be stable beyond all meaningful concern, and most likely this thought should not disturb your sleep, but it should deepen your wonder, because somewhere beneath every calm patch of darkness lies a truth we rarely feel in our bones. The universe does not promise advance notice. It promises only that information travels according to its laws, and sometimes, for the deepest kinds of change, arrival and revelation are the same moment. Why this probably shouldn't keep you awake. Some ideas sound dangerous because they are close, and others sound dangerous because they are too large for the mind to hold. Vacuum decay belongs to the second kind. After hearing that the vacuum might be metastable, that space itself could in theory change state, and that such a change could not send a warning ahead of itself, it is natural for the imagination to tighten. The mind turns a distant theoretical possibility into a shadow beside the bed. It asks, what if it happens now? But this is exactly where careful science becomes calming, because not every terrifying idea is a realistic danger, and not every possible event is meaningful on the scale of a human life. Vacuum decay probably should not keep you awake because the universe has already been awake for a very long time. For about 13.8 billion years, the vacuum has remained stable enough for galaxies to form, for stars to ignite and die, for heavy elements to be made, for planets to cool, for chemistry to become complex, and for life to rise from matter and begin asking whether the vacuum is stable. That enormous history is not proof of absolute safety in the philosophical sense, but it is a powerful clue. If the vacuum were fragile in an ordinary way, if it could easily be tipped into another state by energetic events, the universe would have had countless chances to do so long before human beings ever existed. Nature has been running particle collisions at energies far beyond our machines since before Earth formed. Cosmic rays, some of the most energetic particles known, constantly strike planets, moons, interstellar gas, and dense objects across the universe. The cosmos contains supernovae, neutron stars, black holes, gamma-ray bursts, and environments more extreme than anything built in a laboratory. If familiar high-energy processes could casually trigger vacuum decay, the sky would likely have written that answer already. The fact that stars still shine, atoms still hold, and the vacuum still behaves as it does is part of the reassurance. It does not make the question meaningless, but it places the fear in its proper distance. Physicists do not discuss vacuum decay because they expect it to happen tomorrow. They discuss it because it reveals something deep about the difference between practical danger and theoretical possibility. A bridge can be mathematically analyzed for rare failure modes without anyone suggesting you panic while crossing it. A radioactive atom can have a chance to decay at any moment, but if its half-life is vastly longer than the age of the universe, that chance is not something a human nervous system should treat like a wolf at the door. In the same way, if our vacuum is metastable, many estimates suggest it could be so long-lived that the expected time before decay is unimaginably greater than the current age of the cosmos. Unimaginably here is not a decorative word. It means the scale is so far beyond human time, planetary time, stellar time, and even ordinary cosmic history that fear loses its practical shape. You can understand the idea without carrying it as a burden. This is important because the brain is not naturally good at handling extremely small probabilities attached to extremely dramatic outcomes. It hears possible and feels near. It hears no warning and feels threat. But physics asks for a quieter discipline. Possible does not mean likely. Not forbidden does not mean expected. A theoretical scenario does not become a forecast simply because it is vivid. Many things can be described by equations or imagined within models, but the real question is how probable they are, under what assumptions, and on what timescale. Vacuum stability calculations depend on the measured properties of particles such as the Higgs boson and the top quark, and on the assumption that the standard model remains valid up to extremely high energies. But we already know the standard model is not the final complete story of everything. It does not fully include gravity at the quantum level. It does not explain dark matter. It does not answer why neutrinos have the masses they do, or why the universe contains more matter than antimatter. New physics at very high energies could change the vacuum stability picture entirely. It could make the vacuum more stable than the simplest calculation suggests. It could modify the landscape. It could reveal protective principles we do not yet know. So even the statement, "our vacuum may be metastable," is not a final verdict carved into reality. It is a conditional conclusion within a powerful but incomplete framework. And that should soften the fear. The scariest version of the idea often comes from telling it as if science has discovered a cosmic trapdoor beneath your feet. A more honest version is this. Our best current theories raise a profound question about whether the vacuum state is absolutely stable or merely incredibly long-lived. And the evidence so far gives no reason to treat it as an immediate or ordinary danger. This is not denial, it is proportion. The universe is full of things that matter far more for daily life. Health, climate, human choices, technology, ecosystems, relationships, fragile bodies, limited time. Vacuum decay belongs to the category of deep cosmic questions, not practical threats. It is closer to asking whether space has a final foundation than asking whether tomorrow is safe. And in a strange way, understanding it can even make the world feel more peaceful. If the vacuum is stable enough to hold all of cosmic history so far, then every ordinary moment is happening inside a vast continuity. The light on your wall, the weight of your hand, the steady behavior of atoms, the predictable chemistry of water, the fact that a clock keeps ticking from 1 second to the next. All of it is evidence that the underlying rules are holding. You do not usually notice stability because stability is quiet. You notice danger because danger interrupts. But the vacuum's steadiness is one of the greatest silences in existence. It has allowed the universe to remain coherent long enough for meaning to appear. And perhaps that is the right emotional turn. Vacuum decay should not keep you awake because its value is not in frightening you. Its value is in teaching you how delicate and consistent reality has been. It reveals that empty space is not a trivial background, but it also reveals that this background has endured. The same vacuum whose nature we question is the vacuum that has supported every sunrise, every orbit, every star cluster, every breath ever taken on Earth. To fear it constantly would be like fearing gravity because it can form black holes. Gravity also holds your feet to the ground, keeps the moon near Earth, gathers gas into stars, and allows planets to exist. A deep force can have extreme consequences in theory without being a personal threat in ordinary life. The vacuum is similar. Its hidden structure may contain frightening possibilities at the edge of thought, but its everyday reality is stability. It is the calm condition beneath the storm of visible things. This does not mean scientists stop asking questions. They will continue refining measurements, testing particle properties, searching for new physics, studying the early universe, and asking whether the vacuum is truly stable, metastable, or something our current categories do not yet capture. That curiosity is healthy. It is what turns existential unease into knowledge. The mistake would be to let a rare theoretical possibility become emotional noise, drowning out the more useful wonder, because the real lesson is not the universe could end without warning. The real lesson is the universe depends on deep structures we are only beginning to understand, and those structures have held with astonishing reliability. When you frame it that way, the fear becomes smaller and the awe becomes larger. You begin to see the vacuum not as a hidden assassin, but as a quiet foundation, whose stability is one of the reasons anything can be known at all. If it were constantly changing, no science would be possible. No atoms would keep their identities long enough for chemistry. No stars would follow life cycles. No memory could trust the continuity between yesterday and today. The fact that you can learn about vacuum decay without being consumed by it is itself a tribute to the universe's order. So let this idea settle gently. There are theoretical possibilities so vast that they should humble you, not haunt you. There are cosmic questions so deep that they belong in the mind as wonder, not anxiety. Vacuum decay probably should not keep you awake, because it is not a forecast, not an expected event, not a practical danger waiting in the room. It is a window into the unknown stability of space, a reminder that our world rests on laws still being uncovered, and a sign that even the emptiest thing we can name may have layers beneath it. Tonight the vacuum holds. Atoms keep their shapes. Light keeps traveling. The stars remain visible in the dark. And perhaps that is enough. Not absolute certainty, because science rarely gives that kind of comfort, but a quieter and more honest comfort. The universe has carried itself for billions of years, and in that long calm, you are allowed to sleep. The Higgs field and the hidden stability of reality. The universe feels stable because tables stay solid. Atoms keep their identities, and light behaves today the way it behaved yesterday. But hidden beneath that ordinary trust is a field you never see, never touch, and yet depend on every second. This is the Higgs field, and its importance is often reduced to a single phrase. It gives particles mass, but that phrase is only the doorway, not the room. The deeper idea is that empty space is not simply empty. It has a settled condition, and one of the most important parts of that condition is the value of the Higgs field spread everywhere. Unlike a lamp that turns on in one place or a cloud that drifts through one region, the Higgs field is understood to be present throughout space, quietly filling the universe with the same background value. You do not notice it because it is not a wind pushing on your skin, not a fluid slowing your movement, not a glowing substance between stars. It is more like a hidden setting of reality, a constant background arrangement that certain particles interact with as they move through the world. Some particles interact with this field strongly and behave as if they have more mass. Others interact weakly and have less. The photon, the particle of light, does not acquire mass from the Higgs field in the same way, which is why light can travel freely across cosmic distances. The W and Z bosons, carriers of the weak nuclear force, do interact with the Higgs field in a way that makes them heavy. And because they are heavy, the weak force acts only over extremely tiny distances. That small fact quietly shapes the universe. The weak force is involved in radioactive decay and in the nuclear processes that help stars shine, including transformations that allow the sun to burn steadily instead of behaving like a very different kind of star. So the Higgs field is not just a technical detail in particle physics. It helps explain why the forces of nature have the ranges and behaviors they do. It helps determine why particles are not all massless, why atoms can have the structures they have, and why the physical world is not a featureless rush of light-speed ingredients. But there is an important correction here, because honesty matters. The Higgs field does not provide all mass in the everyday world. Most of the mass of protons and neutrons, and therefore most of the mass in your body, comes not directly from the Higgs field, but from the energy of quarks and gluons bound together by the strong nuclear force. The Higgs field gives mass to fundamental particles like electrons and quarks, but when quarks are locked inside protons and neutrons, the energy of their strong force confinement becomes the dominant part of the mass we experience. This makes the story more interesting, not less. The Higgs field does not single-handedly make everything heavy. Instead, it sets crucial parameters, especially the masses of fundamental particles, and those parameters become part of a larger chain that allows stable matter to exist. If the electron's mass were very different, atoms would have different sizes and chemical behavior. If quark masses were different, the balance inside protons and neutrons could change. If the W and Z bosons were not heavy, the weak force would not be weak in the familiar way, and the nuclear history of stars could be dramatically altered. Reality depends not only on the existence of particles, but on their exact relationships, their masses, their forces, their allowed interactions. The Higgs field is one of the hidden reasons those relationships have the values we observe. And this is where the stability of reality begins to feel almost fragile, not because it is about to fail, but because it is so deeply tuned by invisible conditions. In the early universe, when everything was unimaginably hot, the Higgs field may not have had the settled value it has today. At extremely high temperatures, the universe may have been in a more symmetric state, where the distinction between some forces and particle behaviors was different. As the universe cooled, the Higgs field settled into its present value, a process often described as electroweak symmetry breaking. That phrase sounds abstract, but the meaning is profound. The familiar properties of particles may have emerged as the universe cooled into a new state. The world you know may not have been written into reality from the very first instant in the same form. It may have unfolded as the fields of nature settled. A useful image is water freezing into ice, though the comparison is only a guide. Liquid water and ice are made of the same substance, but their structure changes when conditions change. In a much deeper way, the early universe could pass through changes in field states that alter how particles behave. The Higgs field settling into its current background value is part of how the universe became the kind of universe that can build atoms, chemistry, and eventually living bodies. In 2012, scientists at the Large Hadron Collider discovered the Higgs boson, a particle associated with excitations of the Higgs field. That discovery did not mean they found the field itself in a jar. It meant they detected a ripple of the field, a measurable sign that the field was real in the way the theory predicted. Think of a still lake hidden in darkness. You may not see the whole lake, but if a ripple reaches your instrument, you learn something about the water beneath it. The Higgs boson was that ripple, and its discovery confirmed a major missing piece of the standard model. But confirmation did not close the story. It opened a deeper one. The measured mass of the Higgs boson appears to place our universe in a strange region of theoretical possibility. Perhaps stable, perhaps metastable, depending on precise measurements and on whether unknown physics appears at higher energies. This does not mean the universe is unsafe in any practical sense. It means the shape of the Higgs field's energy landscape may be connected to the long-term stability of the vacuum. The Higgs field has a preferred value, like a ball resting in a valley, and the shape of that valley helps determine whether the vacuum is truly the lowest state or only an extraordinarily long-lived one. But instead of turning this into fear, it is better to see it as a lesson in depth. The stability of the world is not just the stability of rocks and planets, it is the stability of the fields beneath them. The ground under your feet is held together by atoms. Atoms depend on electrons and nuclei. Nuclei depend on the strong and weak forces, and the behavior of fundamental particles depends partly on the Higgs field's quiet presence everywhere. You are standing on layers of stability you cannot feel. You trust the floor, but the floor trusts atoms. The atoms trust fields. The fields trust the vacuum state. And somewhere in that hidden chain, the Higgs field is one of reality's most important agreements. It gives the universe a kind of mass pattern, a way for particles to resist being weightless flashes. a way for the weak force to remain short-ranged, a way for matter to form the structures that make chemistry possible. Without the Higgs field in its present state, the universe might not simply look slightly different. It might be unable to build the same kinds of stars, atoms, molecules, and observers. This does not mean the Higgs field was designed for us, and it does not prove that the universe has intention. It means the universe we inhabit depends on physical conditions that are more hidden and more delicate than everyday life suggests. The most important foundations are often the least visible. You can see a mountain, but not the quantum fields that allow its atoms to exist. You can feel your heartbeat, but not the background value that helps define the particles in your blood. You can watch sunlight cross a room, but not the field arrangement that helps determine why the sun's nuclear reactions proceed in the way they do. The Higgs field is a quiet presence behind all of this, not mystical, not alive, not a cosmic mind, but physically real in the sense that its effects appear in the behavior of particles and in the success of our best theories. And perhaps that is why it feels so powerful as a story. It shows that reality's stability is not loud. It does not need to announce itself. The most essential things may work by remaining almost perfectly unnoticed. If the Higgs field were different, you would not simply point to it and say, "There is the change." Everything built on top of it would change with it. The universe would have a different grammar. Matter would speak a different language. So when you think about the Higgs field, do not imagine a magical substance giving weight like dust settling on particles. Imagine a hidden condition of space, a field whose settled value helps define the properties of the fundamental world. Imagine the universe after its earliest heat, cooling into a form where particles gained the behaviors that made structure possible. Imagine stability not as something obvious, but as a quiet balance maintained beneath every visible thing. The Higgs field and the hidden stability of reality remind us that the world is not only held together by what we can see, it is held together by invisible values, silent fields, and deep agreements in the vacuum. Agreements so steady that we mistake them for nothing, and so important that without them, the familiar universe might never have learned how to become real. Could the rules of physics change if the vacuum changed? The laws of physics feel eternal because every morning the world remembers how to behave. But what if those laws depend on something quieter than the laws themselves? The state of the vacuum beneath them. This is not the idea that reality changes its rules randomly from one day to the next, or that gravity might suddenly forget how to hold a planet, or that atoms are unstable in any practical everyday sense. The ordinary universe is deeply consistent. Light from distant galaxies follows the same broad rules we test in laboratories. Atoms in stars leave spectral fingerprints that match atoms on Earth. The physics we know has held across enormous distances and billions of years. But at a deeper level, modern physics suggests that what we call the rules may not be completely separate from the condition of the fields filling space. A vacuum is not just a blank stage after matter has been removed. It is the settled state of the fields from which particles and forces arise. If that settled state were different, then the properties of particles could be different too. And if the properties of particles changed, the familiar rules of chemistry, nuclear reactions, light and matter might no longer unfold in the same way. Think of reality as a language. The deepest laws may be like grammar, but the vacuum is like the alphabet available to the universe. Change the alphabet, and the grammar may still have structure, but the words it can form become different. In our current vacuum, electrons have a certain mass, quarks have certain masses, forces have certain strengths and ranges, and particles interact in patterns stable enough to build atoms, stars, planets, and minds. But in another possible vacuum state, the background values of fields could shift. A particle that is light here might be heavier there. A force that is short-ranged here might behave differently there. A type of atom that is stable here might not exist there at all. This is why physicists sometimes say that different vacuum states could correspond to different low-energy physics. It does not mean the universe has no laws. It means the visible laws that matter experiences may depend on which deeper state the vacuum occupies. The early universe gives us a real reason to take this seriously. In its first moments, when temperatures were far beyond anything familiar, the universe was not simply a hotter version of today. Some symmetries may have been restored. Fields may not have had the same settled values they have now. As the cosmos expanded and cooled, it likely passed through transitions where the behavior of fields changed. And with those changes, the universe acquired the particle properties we now treat as normal. This is one of the most important lessons of modern cosmology. The laws we experience may have a history, not the deepest principles changing like moods, but the effective rules of the world emerging as the vacuum settled into a particular form. A useful comparison is a material changing phase. Water, ice, and steam are all built from the same molecules, but their large-scale behavior changes dramatically depending on their state. Ice has rigidity. Water flows. Steam expands to fill space. The microscopic ingredients are related, but the world they create feels different, in a much deeper and more fundamental way. A field can settle into different states, and each state can allow different behavior for particles and forces. The comparison is imperfect, because the vacuum is not a liquid and fields are not ordinary substances, but it helps the mind approach the idea. The background state matters. If the vacuum changed, the universe would not merely repaint itself. It might rewrite the conditions under which matter can exist. Imagine a universe where electrons were much heavier, atoms would become smaller, chemistry would shift, molecular bonds could change, and the delicate structures that make life possible might never appear. Imagine a universe where the difference between protons and neutrons changed. Hydrogen might not remain stable in the same way, or stars might not burn through the same pathways. Imagine a universe where the strength of the electromagnetic interaction differed significantly. Atomic structure, light absorption, chemistry, and the behavior of materials could all be altered. You would not simply have the same world with different colors. You might have a universe where the word water has no object to refer to, where carbon chemistry cannot unfold, where stars burn too quickly or not at all, where planets fail to become the stable stages life requires. This is why the question is so powerful. The rules of physics are not just abstract instructions written on a cosmic wall. They are the conditions that decide whether complexity can rise from simplicity, and the vacuum may be part of why those conditions have the values they do. Some theories suggest there may be many possible vacuum states, sometimes described as a landscape, with each valley corresponding to a different way fields can settle. In one valley, particles and forces take one form. In another, they may take another. We do not know whether all such possibilities are physically real, whether they exist in other regions beyond observation, or whether they are only mathematical possibilities inside our theories. But the idea itself is important because it changes the way we ask questions. Instead of only asking, what are the laws? We also ask, why this vacuum, and therefore why these laws as we experience them? The answer may involve deep necessity. It may involve unknown symmetry. It may involve the history of the early universe. It may involve physics beyond the standard model. Or it may involve possibilities we have not yet learned how to describe. What matters is that the vacuum is no longer just the absence of matter. It becomes part of the explanation for why matter has its familiar character. And this does not make science less reliable. In fact, it shows how precise science has become. We can observe that the laws around us are consistent to extraordinary accuracy. We can test atoms, measure particle masses, study light from distant objects, and confirm that the universe has behaved in a coherent way across cosmic time. The possibility of a different vacuum does not weaken that consistency. It deepens the question beneath it. It says, perhaps the laws are stable because the vacuum state is stable. Perhaps the rules we trust are the rules of this settled phase of reality. If the phase changed, the effective behavior could change too. This is very different from saying anything can happen. Physics is not chaos wearing a mask. A different vacuum would not be a lawless dream. It would have its own structure, its own allowed particles, its own patterns of interaction, perhaps its own version of order. But it might be an order hostile to everything we recognize. Inside such a state, atoms as we know them might fail. Light might interact differently, matter might lose its familiar stability, and the concepts that organize your world, body, planet, star, chemistry, memory, could become impossible. That is why vacuum change is such a profound idea. It does not threaten one object inside reality. It challenges the continuity of the definitions by which objects exist. And yet, it should be approached with calm. There is no evidence that the vacuum around us is changing in a way that affects daily life. The universe has shown remarkable stability. The point is not to frighten the listener, but to reveal the hidden dependency of the visible world. You live inside a set of rules so steady that they feel inevitable. But physics teaches that inevitability may be an illusion born from familiarity. The world feels necessary because it is the only world you have experienced. But the deeper theories whisper that other forms of physical order may be possible, and that our universe is one particular realization of a more mysterious structure. This thought can be unsettling, but it can also be beautiful. It means that every stable atom is a sign of a deeper agreement. Every chemical bond is a consequence of fields having the right settled values. Every star is a fire permitted by the vacuum's hidden arrangement. Every breath you take depends on the universe not merely having laws, but having these laws in this vacuum, with these particles, these forces, and this fragile balance of possibility. So if the vacuum changed, could the rules of physics change? In the deepest sense, the underlying principles might remain, but the world built from them could become unrecognizable. The rules experienced by matter could shift, because matter itself would be redefined by the new state of the fields. That is the honest answer. Not fantasy, not certainty, but a serious possibility in the language of modern physics. And perhaps the final lesson is this: reality is not only held together by what exists, but by the background condition that lets existence take its familiar form. The vacuum is not an empty page. It is the quiet choice of ink, paper, and alphabet. Change it, and the story may still be written, but it would no longer be the story that contains us. Why empty space is more like a system than a background. For centuries, space was treated like the empty page beneath the universe. But the deeper story is that the page can bend, stretch, carry rules, store conditions, and change what the words are able to mean. That is why empty space is more like a system than a background. A background is passive. It sits behind the real action. It does not answer back. It does not care whether a star is born, whether a galaxy turns, whether a particle appears, whether light crosses a billion years of darkness. But the space described by modern physics is not so silent in that simple way. It has geometry, and geometry tells matter how to move. It has causal structure, meaning it helps decide which events can influence which other events. It has horizons, regions beyond which information cannot reach an observer. It has field states, boundary conditions, symmetries, and possible phases. These are not decorations placed on top of emptiness. They are part of what emptiness physically is. In older thinking, space was imagined almost like a stage in a theater. The actors were matter and light. The stage was just there, flat and indifferent, waiting for the performance. But in the universe we actually study, the stage is not merely holding the actors. It can tilt their paths, change the timing of their motions, decide how signals travel, and evolve along with the performance. This is the shift that makes the vacuum feel so profound. It is not only the lack of visible matter, it is a state of the entire physical arrangement. If you remove the planets, stars, gas, dust, and radiation from your imagination, you have not removed the deeper structure that says what distance means, what time means, what counts as a possible path, what can be measured, and how fields behave when they are in their lowest condition. A system is not defined only by what it contains. It is defined by how its parts relate, what rules constrain them, what states it can occupy, how it responds when conditions change, and what patterns remain even when the obvious pieces are gone. In that sense, empty space behaves much more like a system. It has a present condition. It can be curved by energy and momentum. It can carry gravitational waves, tiny ripples in space-time, produced when massive objects accelerate violently, such as merging black holes or neutron stars. Those waves do not travel through space like sound through air. They are changes in the geometry of space-time itself spreading outward. When detectors on Earth measure them, they are not hearing a normal vibration in a material medium. They are detecting the stretching and squeezing of distance itself by an almost unimaginably small amount. That alone tells you space is not a dead container. A container does not usually wave. A background does not usually arrive at your instrument carrying news from a collision that happened far away. Space-time can, and it does so while obeying strict physical laws, not as a mystical fabric, but as a dynamical part of reality. The same is true when you think about time. Time is not merely a universal clock ticking identically everywhere. In relativity, the rate at which time passes depends on motion and gravity. Clocks at different heights in Earth's gravitational field tick at slightly different rates. This is not a philosophical mood. It is measured and accounted for in technologies like GPS, where satellite clocks must be corrected because they do not experience time exactly the same way as clocks on Earth's surface. That means the structure of space-time enters practical life quietly, through navigation, communication, and the precision of clocks. If space were only a passive background, time would not behave like that. But if space-time is a physical system, then clocks become local participants in that system. They do not float above reality, measuring it from outside. They are inside it, shaped by the same geometry they help reveal. And this is where the idea becomes larger than any single example. Empty space is more like a system because it has relationships built into it before objects even arrive. It decides what near and far mean. It decides what counts as a straight path. It decides whether two events can exchange information. It decides how light cones open, how horizons form, how distances change, and how matter experiences motion. Even the word empty becomes incomplete because a system can be empty of objects and still rich in structure. Think of a chessboard with no pieces on it. It looks empty, but the rules are already present. Squares have relationships. Moves are possible or impossible. The board is not the game by itself, but it defines what kind of game can occur. Empty space is far deeper than a chessboard, of course, but the lesson is similar. Absence of pieces does not mean absence of structure. The vacuum is not a board made for one game only. It is closer to the underlying condition that lets every physical game be played at all. In quantum field theory, the vacuum is a state, not a blank. In relativity, space-time is a geometry that can respond, not a rigid box. In cosmology, the large-scale behavior of space helps determine the history and future of the universe, not merely the positions of objects inside it. And in all of these views, empty space becomes something with character. It can be stable, or in speculative theories, only long-lived. It can have properties that influence the motion of light and matter. It can contain horizons that limit knowledge. It can expand, cool radiation, separate galaxies, and preserve ancient signals until they arrive at a telescope billions of years later. None of this means space has intention. It does not think. It does not choose. It does not secretly want anything. Calling it a system does not make it alive. It simply means it is active in the scientific sense. It has states, laws, constraints, and responses. And perhaps that is more unsettling than calling it alive, because it means the universe does not need a mind behind the curtain to be deep. The depth is already in the physical structure. The rules are not painted onto reality after the fact. They are woven into the way space itself is described. This also changes how you think about objects. A planet is not just a planet placed somewhere. Its somewhere is part of its story. A beam of light is not just a beam moving across a void. Its path depends on the geometry through which it travels. A particle is not just a tiny thing in an empty room. It belongs to fields whose lowest state is part of the room's identity. An observer is not outside the system looking in. You too are inside the same structure, measuring reality with clocks, eyes, instruments, and thoughts that are themselves made from matter, obeying the rules of the system. There is no clean separation between the visible objects and the invisible order that makes them possible. The world is not divided into things and empty backdrop. It is a layered whole, where the backdrop has behavior and the things are patterns within it. This is why the phrase empty space can be misleading. It sounds like a place where the story pauses, but physics keeps showing that the pause has grammar. It has a way of holding silence. It has rules for what can happen next. It has a memory of the universe's expansion in the light that travels through it. It has geometry shaped by what exists and by how energy is arranged. It has a quantum state beneath the particles that come and go. It has a deep connection to the unanswered question of how gravity and quantum theory fit together. If the two greatest descriptions of reality meet anywhere, they meet in the question of what space is when you stop treating it as a background and start treating it as a physical system. Is space-time fundamental, or does it emerge from something deeper? Are distances basic, or are they produced by hidden relationships? Does the vacuum have layers of structure below the fields we know? These are open questions, and they matter because they point beyond the visible universe into the foundation of explanation itself. Still, the most important idea is simple enough to carry gently. Empty space is not merely where things happen. It is part of why things happen the way they do. It is the quiet order that gives motion a path, light a route, clocks a rhythm, fields a state, and events a relationship to one another. When you look at a dark patch of sky, you are not looking at a useless background behind the real cosmos. You are looking into the system that lets the cosmos be readable. The stars may catch your eye, but the space between them carries the deeper architecture. It holds the rules of distance, the limits of communication, the conditions of fields, the possibility of curvature, the shape of cosmic history. And maybe that is the thought that should remain when the voice grows quiet. The universe is not built on a passive emptiness. It is built on a living-like, but not living system of invisible structure. A calm foundation that never appears as an object, yet allows every object to appear. Empty space is more than a background, because a background can be ignored. This cannot. It is the hidden system beneath the visible world, and every star, atom, clock, and thought is moving inside its silence. The universe is built on what looks like nothing. If you erased every star from the sky, every planet from its orbit, every atom from every cloud of gas, the universe would not become meaningless. It would reveal the hidden framework that made all of those things possible in the first place. That is the strange truth behind the idea that the universe is built on what looks like nothing. We usually think of reality as a collection of visible objects: suns, moons, galaxies, stones, oceans, bodies, machines, dust, fire, light. These are the things the senses can follow. They have edges, colors, weight, temperature, motion. They give the mind something to hold. But physics keeps pointing toward a deeper kind of foundation, one that does not look like an object at all. Beneath the visible world are conditions, fields, symmetries, conservation laws, causal limits, and background states that do not appear as furniture inside the universe, but decide what kind of furniture can exist. A brick house is not built only from bricks. It is also built from rules of strength, pressure, balance, shape, and connection. In the same way, the cosmos is not built only from matter. It is built from the invisible order that tells matter how to behave. This is why nothing is such a dangerous word. It makes the mind lazy. It points to a dark gap and says there is nothing there because there is nothing obvious there. But the absence of obvious things is not the absence of structure. A silent computer screen may still be running code beneath the darkness. A blank page may still belong to a language, a writer, a grammar, a history of meaning waiting to appear. A quiet room may still have dimensions, temperature, gravity, electromagnetic conditions, and time passing through it. What looks like nothing is often simply the layer our senses are not designed to read. The universe, at its deepest known levels, seems to be built from such unreadable layers. Consider the importance of conservation laws. Energy, momentum, electric charge. These are not objects you can point to like stones. They are principles. Patterns of accounting nature follows with astonishing consistency. When a particle interaction happens, something visible may emerge or vanish. but the deeper quantities remain balanced according to rules. These rules are tied, in modern physics, to symmetries, ways nature behaves the same under certain changes. The idea is subtle but powerful. If the laws of physics do not change from one moment to the next, there is a connection to energy conservation. If the laws are the same from one place to another, there is a connection to momentum. These are not decorative ideas. They are part of the invisible architecture beneath every event. You do not see symmetry floating between stars. But without such hidden sameness, the universe would not have the reliability needed for matter, motion, clocks, or memory. Reality is not only made of things, it is made of things that keep promises. An atom remains an atom because the rules do not shift randomly. A star shines for billions of years because nuclear reactions obey stable patterns. A telescope can study a galaxy whose light traveled for ages because the behavior of light did not change completely along the way. That reliability is not a visible substance, yet everything visible depends on it. This is what it means to be built on what looks like nothing. The foundation is not always material. Sometimes the foundation is consistency, and consistency can be more fundamental than any single object inside it. Another example is dimensionality. You live in a world where space has 3 large dimensions of movement, and time has a direction your mind experiences as past flowing toward future. You cannot pick up dimensionality. You cannot weigh it. It is not a planet or a particle, but change the number or character of dimensions, and the whole universe could become unrecognizable. Stable orbits, waves, fields, geometry, and even the possible complexity of structures depend on the kind of space-time reality provides. This means the emptiest seeming feature, the way room itself is organized, may be one of the most important ingredients of all. A universe is not only defined by what fills it, but by what kind of where and when it has. Without a structure of distance, no object can be separated from another. Without time, no change can unfold. Without causal order, no event can lead to another in a reliable way. These are not things floating inside the cosmos. They are the deep permission system that lets a cosmos have a story. And this permission system is so familiar that it becomes invisible. You do not notice that space lets you move, that time lets events differ, that causality lets memory point backward and expectation point forward. You simply live inside those permissions and call them normal. But normal is not the same as simple. The most ordinary assumptions may be the deepest gifts. In the early universe, this hidden order mattered before there were planets, before there were stars, before there were atoms in the familiar sense. The universe began in a hot, dense state where matter and radiation behaved very differently from the calm world you know now. As it expanded and cooled, structures gradually became possible. First simple particles in stable forms, then nuclei, then atoms, then clouds of gas, then stars and galaxies. But none of that could happen without the underlying rules already allowing stability, interaction, cooling, attraction, and transformation. Matter did not build the universe alone. Matter followed a script written in fields and laws. The first stars were not just piles of hydrogen collapsing because hydrogen happened to exist. They were the result of gravity, thermodynamics, nuclear physics, radiation, and time working together across a background that allowed differences to grow. Tiny variations in the early universe became seeds for later structure. Regions slightly denser than others pulled in more matter, forming the first cosmic architecture. Those differences were small, almost ghost-like, compared with the enormous structures they eventually produced. But gravity patiently amplified them. In that sense, the universe was built not only from substance, but from imbalance, from tiny departures, from perfect smoothness. If everything had been absolutely uniform, with no differences anywhere, structure might never have formed in the same way. The richness of the cosmos came from the fact that almost nothing was not exactly nothing. A slight pattern became a galaxy, a slight density difference became a future cluster, a faint early irregularity became the scaffolding for stars. This is one of the most beautiful lessons in cosmology. The universe does not always need a large beginning to make a large result. Given time and law, the smallest unevenness can become a continent of light, and the same theme appears inside matter itself. The physical world is built not only from particles, but from the allowed relationships between them. A proton is not merely a bag of tiny pieces. It is a stable pattern of energy and interaction held together by the strong force. An atom is not merely a nucleus with an electron nearby. It is a structured set of allowed states. A molecule is not just atoms touching. It is a relationship of shared and arranged electrons shaped by quantum rules. Your body is not only a collection of elements. It is organization, information, chemistry, boundary, flow, memory, and repair. Life itself shows how much can be built from pattern. The atoms in a living cell are not rare compared with atoms elsewhere in the universe. Carbon, hydrogen, oxygen, nitrogen. These are not magical ingredients by themselves. What matters is how they are arranged, how energy moves through them, how information is stored, copied, corrected, and expressed. A living thing is matter organized so deeply that it begins to maintain itself. That organization is not visible as a separate object. You cannot scoop pattern into your hand apart from the matter carrying it, but without pattern, the matter would not be alive. Here again, what looks like nothing, arrangement, relation, instruction, sequence, becomes the difference between dust and breath. The universe is built on layers like this. At the bottom of ordinary experience, you find not hard final objects, but relationships and rules. At the largest scales, you find not a static arena, but an evolving geometry. At the smaller scales, you find not tiny solid beads, but fields, probabilities, and allowed interactions. At the level of life, you find not a mysterious substance added to matter, but matter organized through information and energy flow. This does not make reality less real. It makes reality more astonishing. It means the visible world is the surface expression of invisible structure. A tree is sunlight, water, carbon, time, genetic instruction, cellular machinery, and physical law braided into a shape that can grow. A star is gravity, pressure, nuclear fusion, radiation, and balance held for millions or billions of years. A human thought is chemistry and electricity arranged into experience so private that the universe seems to look back at itself through your awareness. None of these things would exist if the deeper invisible conditions were not steady enough to support them. So when we say the universe is built on what looks like nothing, we are not saying it is unreal. We are saying its foundation is not always theatrical. The deepest supports do not glow. They do not make noise. They do not stand before you like monuments. They are more like grammar than speech, more like a riverbed than the river, more like silence shaping the music than the note itself. And perhaps this is why the idea feels so calming and so vast at the same time. The most dangerous thing may be the thing everywhere at once. A danger with an address can be avoided, but a danger that is everywhere does not need to move toward you. That is the deeper meaning behind the idea that the most dangerous thing may be the thing everywhere at once. A black hole has a location, a supernova has a star, a gamma ray burst has a direction. Even the most violent objects in the universe are, in some sense, local. They happen somewhere, and if you are far enough away, distance becomes protection. But the vacuum is different. Empty space is not an object sitting in one corner of the cosmos. It is not a storm you can fly around. Not a fire you can watch from a safe hill, not a monster hidden between two galaxies. It is the shared condition underneath every room, every orbit, every atom, every galaxy, every quiet breath. If something is local, the universe can survive it somewhere else. A star can explode and other stars continue burning. A planet can break and other planets remain whole. A galaxy can collide and the wider cosmos goes on. But if the deepest properties of space itself matter, then there is no somewhere else outside their influence. That is why the vacuum can feel more dangerous than a dramatic cosmic object. Not because it is aggressive, but because it is universal. Its power is not in attacking. Its power is in being the condition everything already depends on. Think about the difference between a cracked window and a changed atmosphere. A cracked window is a problem in one place. You can step away from it. You can repair it. But if the air itself changed everywhere, every breath would become part of the problem. The vacuum is even more fundamental than air. It is not what you breathe. It is part of the underlying state in which breathing, chemistry, light, and matter have their familiar meanings. This is why small properties can become enormous when they are spread everywhere. A tiny local effect may be almost irrelevant, but a tiny universal property can shape the whole future because it is repeated in every volume of space, in every direction, at every scale. The universe often hides its deepest power inside things that seem weak in one place, but decisive across everything. Gravity is weak compared with other forces at the level of particles. And yet across planets, stars, galaxies, and cosmic time, it builds the large-scale architecture of the universe because it reaches far and accumulates. In a similar emotional sense, the vacuum does not need to feel powerful in your hand to be cosmically important. You do not feel it as pressure on your skin. You do not hear it humming beneath the floor. You do not wake in the night because space is visibly doing something around you. But the absence of sensation is not the absence of influence. Some of the most important features of reality are invisible precisely because they are too constant. You notice a light switching on, but not the electrical rules that allow switches to work. You notice a door closing, but not the geometry that lets space have distance. You notice matter, but not the background conditions that allow matter to keep the same identity from one second to the next. The vacuum is like that. It is so common that the mind mistakes it for nothing. It is so stable that we mistake stability for simplicity. And yet, a universal background condition can become the most important thing in existence because every other thing is built inside it. This is not a claim that the vacuum is waiting to harm us. It is not a warning that everyday life is unsafe. The point is more thoughtful and more unsettling. The deepest risks in physics are often not like disasters inside the world, but like changes to the assumptions that make the world possible. If a star dies, the laws remain. If a planet freezes, the laws remain. If a galaxy drifts beyond reach, the laws remain. But if the properties of the vacuum were different, then the familiar behavior of particles, forces, and atoms could be different with it. That is why physicists care so much about background fields, constants, symmetry breaking, and vacuum stability. They are not studying empty space because it looks dramatic. They are studying it because the visible world may be downstream from invisible settings. The masses of fundamental particles, the range of certain forces, the structure of atoms, the possibility of chemistry, the way light interacts with matter. All of these belong to a universe whose vacuum has a particular state. Change the state enough, and you may not simply change one object. You may change the rule environment in which objects make sense. This is what makes everywhere at once such a powerful phrase. A local danger competes with the rest of reality. A universal condition defines the rest of reality. It is the difference between a bad note inside a song and a change in the tuning system of the instrument itself. If one string breaks, the music suffers. If the rules of tuning change everywhere, the entire meaning of harmony changes. And still, this should be held calmly. The universe has displayed extraordinary consistency. The atoms in distant stars behave in ways we can compare with atoms on Earth. Light from ancient galaxies carries patterns that tell us the same broad physics has operated across immense stretches of space and time. The vacuum around us has remained stable enough for cosmic history to unfold with patience. First simple particles, then atoms, then stars, then heavy elements, then planets, then life, then a mind capable of worrying about the vacuum. That long stability is not a small comfort. It is the reason science is possible at all. If the background rules were flickering unpredictably, there would be no reliable universe to understand. So the danger here is not practical panic, it is conceptual depth. The vacuum is dangerous in the same way a foundation is dangerous if you realize the whole building depends on it. You do not fear the foundation every morning because it has held for years, but you respect it because without it, the walls are only temporary shapes. Empty space is the foundation that does not look like one. It does not sit beneath the universe as a stone slab. It surrounds and permeates the universe as its underlying condition. This is why the most dangerous thing may be the thing everywhere at once, because there is no boundary around it, no safe distance from it, no outside perspective from which it becomes someone else's problem. It is under the stars and between them. It is in the space inside galaxies and in the vast distances beyond them. It is around atoms and between planets. It is not a thing you approach. It is the condition you are already inside, and that turns the usual logic of danger upside down. We are trained to fear what moves, what strikes, what burns, what breaks. But the vacuum suggests a quieter category of power. What defines, what permits, what remains constant, what silently decides the range of possibility. A knife is dangerous because it can cut. A star is dangerous because it can explode. Space is dangerous in this deeper sense, because if its hidden properties matter, then they matter everywhere reality exists. The smallest change in a universal rule can have consequences no local explosion could match. Not because it is violent, but because it is foundational. And perhaps that is why this idea belongs near the end of the story. After all the talk of fields, pressure, dark energy, expansion, vacuum stability, and the fate of atoms, the lesson is not that empty space is a villain. The lesson is that the quietest background in your imagination may be the widest influence in the universe. It is everywhere, and because it is everywhere, even its gentlest properties can become cosmic. The void does not need claws. It does not need hunger. It does not need intention. It only needs to be the ground on which every visible thing stands. So when you look into the darkness between stars, try to feel the reversal. The dangerous thing may not be the bright explosion, the collapsing star, or the gravitational abyss. Those are events inside reality. The deeper power may be the condition that lets events exist at all. Empty space looks harmless because it is silent, but its silence is universal, and universal things do not need to be loud to decide the fate of everything. The void was never empty. The word void sounds like the final name for absence, but the more we study the universe, the more it begins to look like a human misunderstanding of something far deeper. We gave the darkness between things a simple label because our eyes could not find anything to hold there. No flames, no stones, no oceans, no walls, no visible machinery. Just distance, just silence, just the black interval between stars. And for a long time, that seemed reasonable. If something did not shine, resist, speak, fall, burn, or cast a shadow, the mind placed it in the category of nothing. But physics has slowly taught us that the universe is not obligated to match the categories of the human mind. The void was never empty, because emptiness in the universe is not the same as non-existence. It is not a blank deletion where reality has been removed. It is a condition, a stage, a structure, a field-filled quietness, where the deepest rules remain active even when the obvious actors are gone. If you remove the air from a chamber, you have not removed space. If you remove the dust from space, you have not removed the fields. If you remove the particles from the fields, you have not removed the laws that define what a particle could be. If you remove every visible thing from your imagination, you still have a question left behind. What is the thing that allows visibility, motion, distance, time, energy, and matter to mean anything at all? That question is the true face of the void. Not a monster, not a magical ocean, not a cosmic personality hiding in the dark, but the hidden condition beneath all visible events. This is why the journey through empty space changes the way you see everything else. At first, the void looks peaceful because it does not demand attention. Stars demand attention. Black holes demand attention. Explosions demand attention. But the void does something more subtle. It provides the context in which attention becomes possible. It holds the distances that let galaxies be separate. It carries the fields whose excitations can appear as particles. It has geometry, so light can cross it and gravity can shape paths through it. It has a quantum state, so even the lowest condition of reality is not the same as a dead, classical blank. It can be stretched by cosmic expansion, and that stretching changes the temperature, visibility, and future of the universe. It can be described with pressure-like behavior on cosmic scales, and that behavior may be tied to the accelerated expansion that slowly carries distant galaxies beyond reach. It can leave tiny marks in atoms, subtle enough to require precise experiments, yet real enough to force theories to become deeper. It can be constrained by boundaries and reveal forces where ordinary intuition expects nothing. It can raise questions about stability, about whether the vacuum state of our universe is final or only extraordinarily long-lived. And perhaps most importantly, it teaches that absence is not always simple. The places where the senses report nothing may still be filled with permission, limitation, possibility, and law. This is not an invitation to exaggerate. The void is not full in the way a room is full of furniture. It is not crowded with tiny invisible marbles waiting to be seen. It does not offer unlimited energy. It does not prove mystical shortcuts or secret intentions. The real story is more disciplined and more beautiful than that. What we call empty space is empty of ordinary matter, but not empty of physical meaning. It is the lowest known condition of fields, the quiet arrangement through which matter and light acquire their behavior. In one sense, the universe is made of things. In another, deeper sense, it is made of what things are allowed to do. The void belongs to that second layer. It is not the sculpture, it is the rules of the material, the balance of forces, the shape of the room, the silence that decides how sound will travel when a note is finally played. And if this feels abstract, bring it closer. The atoms in your body do not exist in isolation from the rest of physics. Their structure depends on quantum rules. Their particles depend on fields. Their stability depends on the vacuum state being what it is. The light entering your eyes is not merely traveling through darkness. It is following the geometry of space-time and the behavior of electromagnetic fields. The galaxies you see in telescope images are not simply sitting in a black background. They are embedded in an expanding cosmic history where space itself participates in the story. Even your sense of solidity, your sense that the world has dependable shape, rests on invisible conditions that have remained stable long enough for chemistry, biology, memory, and wonder to arise. So the void is not far away. It is not only between galaxies. It is around every atom, inside every room, beneath every ordinary moment that feels too familiar to question. The quiet space around your hand is part of the same physical reality as the dark between stars. The vacuum does not become important only when it is enormous. It is important because it is the background condition everywhere, from the smallest interactions to the largest fate of the cosmos. And this is where the title becomes clear. The void was never empty because the universe was never built from objects alone. It was built from relationships, fields, states, symmetries, distances, constraints, and histories. It was built from laws that remained even when no eye watched them. It was built from a ground so quiet that generations mistook it for nothing, and so powerful that the smallest change in it could reshape everything. The ancient darkness above us is not a lack of story. It is the oldest page of the story, written in a language almost too quiet to notice. The stars are bright punctuation marks, but the spaces between them carry the grammar. And maybe this is the final lesson the listener should keep while drifting towards sleep. The universe's deepest mystery may not be hidden only in the places that shine. It may be hidden in the calm between them, in the silence that lets light travel, in the invisible fields that let particles exist, in the vacuum state that lets matter remain stable, in the expanding distance that slowly changes the future. We began by thinking of empty space as a blank. We end by seeing it as the foundation beneath the visible world. Not dangerous because it attacks, not frightening because it roars, but powerful because it is everywhere, and because everything depends on what it quietly is. The void was never empty. It was the unseen ground of reality all along. The stillness beneath motion, the darkness that lets stars appear, the silence between notes that allows the music of the universe to be heard.